Good morning, everyone. Welcome to the first virtual data gathering workshop for the committee to review the dietary reference intakes for energy. I'm Ann Yaktine. I'm the study director and the director of the Food Nutrition Board, and I'm going to turn the meeting over to the committee chair, Dr. Ana Maria Ciega-Rees.
Thank you, Ann. And it's my pleasure to welcome everybody to this open session for the committee to review the DRIs for energy. As Ann said, I'm Ana Maria Ciega-Rees. I'm chair of this committee and this study. I'm the dean of the School of Public Health and Health Sciences at the University of Amherst, the University of Massachusetts at Amherst. The task being undertaken by this committee of the National Academies of Sciences, Engineering, and Medicine is to assess human requirements for energy intake and energy expenditure. This meeting is being held to gather information to help the committee conduct its study. That is, the committee is in the process of assembling materials that it will examine and discuss in the course of making its findings, conclusions, and recommendations. Therefore, I ask everyone here today to be extremely mindful of the fact that the committee has made no conclusions and that it would be a mistake for anyone to leave here today thinking otherwise. Comments made by individuals, including members of the committee, should not be interpreted as positions of the committee or the National Academies. In addition, please note that committee members typically ask probing questions, and in these information gathering sessions may not be indicative of their personal views. The committee will deliberate thoroughly before writing its draft report. Moreover, once the draft report is written, it must go through a very rigorous review by experts who are anonymous to the committee, and then the committee must respond to this review with appropriate revisions that adequately satisfy the National Academies Report Review Committee and the National Academy of Sciences president before it is considered an official report of the Academy. So today, I want to remind everybody that the committee will not be entertaining questions from the audience. And that's very important to keep in mind. This session, the full day session, will be available at the website. So you'll be able to view it after the meeting. I am now going to ask each of my committee members, fellow committee members, to please introduce themselves, their name and their institution. So let's see, I think I'll call you so that you know how to get started here. Dr. Reagan Bailey.
Hi, everyone. My camera is disabled, so I don't know why I can't connect to the video, but I am the Associate Director of Precision Nutrition at the Institute for Advancing Health Through Agriculture at Texas A&M University. There I am.
There you are. Wonderful. Dr. Ethan Bach.
Sorry about that. Hello, Ethan Bach. I'm Associate Professor in the Center of Evidence Synthesis and Health at the Brown University School of Public Health.
Thank you, Ethan. Dr. Susan Barr.
Morning, everyone. I'm Susan Barr from the University of British Columbia in Vancouver, Canada, and I'm Professor Emeritus.
Thank you. Dr. Lonica Blackman-Carr.
Lonica is ill today, so she won't be with us. I'm sorry, I didn't tell you that.
Okay, thank you. Dr. Nancy Butte.
Hi, I'm also blocked as well, but I'm Nancy Butte. I'm an emeritus professor from Baylor College of Medicine, Department of Pediatrics.
Thank you, Nancy. Dr. Amy Luke.
Hi, everyone. I'm Amy Luke. I'm professor and chair of the Department of Public Health Sciences at Loyola University, Chicago.
Thank you. Dr. Susan Roberts. Susan not on.
You're on mute, Susan.
Yeah. Hi, everybody. I'm Susan Roberts. I am Director of the Energy Metabolism Laboratory at the USDA Human Nutrition Research Center at Tufts University, Professor of Nutrition at Tufts, Professor of Psychiatry at Tufts Medical Center, and co-director of the Tufts Institute for Global Obesity Research.
Thank you. Dr. Heidi Silver.
Good morning. I'm at Vanderbilt University Medical Center in Nashville, Tennessee, where I am a professor in the Department of Medicine, a director of the Vanderbilt Diet, Body Composition, and Human Metabolism Core, and a health scientist with the Department of Veterans Affairs.
Dr. Scott Crowder.
Hi, Scott Crowder. I'm an associate professor in the Department of Kinesiology, Recreation, and Sports Studies at University of Tennessee. And I'm also the director of our Applied Physiology Lab.
Great, thank you. Dr. Janet Tews.
Hi, I'm Janet Tews. I'm a professor of biostatistics and data science at Wake Forest School of Medicine.
Thank you. And Dr. Elizabeth Yetley.
Hi, I retired from NIH where I was a senior nutrition research scientist.
Thank you. So that is our committee. So thank you very much for providing your introductions. And now I'm going to let Dr. Amy Luke introduce our speaker and take over from here.
Great, thank you, Anna Maria. I'm really happy to introduce Professor John Speakman. John is at the Institute of Biological and Environmental Sciences at the University of Aberdeen in Scotland, and he'll be our first speaker today. And he is going to talk about the use of doubly labeled water to support analysis of energy requirements. So John, I turn it over to you.
Okay, great. Thanks very much, Amy, for that introduction. And also thanks to the committee for asking me to present to you today. So I'm going to share my screen and let's hope this works. I'm hoping you have that now. Okay, great. Okay, so in addition to being at the University of Aberdeen, I also have positions in China where I run another lab. So I'm mostly at the Shenzhen Institute of Advanced Technology where I am at the moment. And so what I'm going to talk about is using doubly labeled water to support analysis of daily energy requirements. I guess that most of you are familiar with the doubly labeled water technique, so I don't have to go into it in any real detail, but I'll just point out that it's an isotope-based method that requires the subject drinks a dose of doubly labeled water, which contains both deuterium and oxygen 18. That floods into the body, so the enrichment in the body water goes up to a peak when it reaches isotopic equilibration, and then it's slowly washed out of the body over a period of about 14 days. And the whole basis of the technique is the fact that the deuterium washes out of the body slightly slower than the oxygen 18, and the difference between those two washouts allows us to estimate CO2 production. And a real benefit of the method is that between the first day when you take the sample here and the last day when you take the sample over here, the subject can go about their daily life. So this is the only technique that really allows you to get an idea of what's happening to energy expenditure for free living subjects completely unencumbered by any apparatus. And that's the real benefit of this method. If you do want to find out more about it, there's an absolutely fantastic book that you can buy. It's a little expensive. It's about $600, but it will tell you everything you need to know about the method. So here we are wanting to know the daily requirements for energy. And I thought it might be good just to track the path between our energy intake and down here, the measurement of CO2 production by doubly labeled water, because they're not the same thing, obviously. This technique is measuring how much CO2 we produce over 2 weeks. And what we really want to know is the daily requirements for energy. So I thought it would be just good to map out the route where we get from energy intake down to CO2 production to show you why this technique can be useful. So when we take in energy, that energy is partitioned in 2 ways. Some of it's absorbed by our gut, comes into our body, and the rest of it is lost as feces. So there's an immediate difference between our energy intake and what our bodies actually have available. And then that energy that's absorbed by the body, there are further losses of energy in our urine. And what's left after the urine losses is what's called the metabolizable energy intake. And that's the energy that's kind of available for us to use. So the first thing that we have to take into account if we're trying to get from here back up to here is this loss in feces and loss in urine. And data in the food energy content tables partially take this into account. And I say partially because actually what they do is they assume that everybody has exactly the same assimilation efficiency, which is a pretty unrealistic assumption, but it's an assumption that's baked into the whole way that this is done. So that's one thing to always bear in mind, is that we're working on an average number for these things, when in fact it's likely that individuals vary. And we don't really know what causes that variability at the moment. So what then happens to this metabolizable energy intake? Well, again, it has two fates. It can either be used to support our daily total energy expenditure, which is what we're really trying to get at, our daily requirements for energy, or it can be diverted into fat stores. So metabolizable energy intake is not directly equivalent to daily total energy expenditure. If we're in a surplus, then some will be diverted into fat. And equally, if we're taking in insufficient to meet our needs, then withdrawal from fat supplies that difference over here. So we can only really estimate daily total energy expenditure in a situation where the individual is in energy balance. And at that point, then metabolizable energy intake is equal to the total daily energy expenditure. And so that's also a condition that we need to think about when we're trying to estimate these things. So how do we get from CO2 production to total daily energy expenditure? Well, there's one more step that we need to know, and that is we need to know the respiratory quotient. And if we can estimate the respiratory quotient, then there's an equation that was derived in 1949 by Weir that allows us to make a direct conversion from CO2 production to daily energy expenditure. And one big advantage of this double labeled water method is that it gives us an estimate over a 2-week period. And the benefit of that is that generally individuals over periods of about 2 weeks are in energy balance. So by using double labeled water to estimate total daily energy expenditure, we kind of are much more likely to meet this requirement over here that the individual is in energy balance, much more likely than if we try and measure energy intake over 24-hour periods, for example. So it's a great technique, but unfortunately it's expensive to use. And so most studies have tended to have sample sizes that are too small to address big issues like defining dietary energy requirements. And there's lots of other big issues as well, of course, that the technique could answer, but generally the sample sizes are too small. So about 5 years ago, the main people that use this method were all together at a meeting in Japan. And we discussed after that meeting whether we should try and pull together all the data that was available in the literature to get a big database where we could then try and start to address those big kind of issues. And I played a major role in organizing the compilation of that database, and I'm currently chairman of this database management group. And this is a group of scientists, many of whom will be familiar to you as experts in the field of energy metabolism. Early on in the sort of genesis of this database, we approached the International Atomic Energy Agency and asked them if they would host it, and they said that they would do. And there's also 2 members from IAEA that are on the management committee as well. You can get to the database through this double labeled water dowdatabase.org. This is a kind of back door into the IAEA database. And the reason that we have a back door is because we have some commercial sponsors, but the IAEA don't allow commercial sponsorship on their site. And so the sponsors are only listed at the back door. So what I'm going to do in this talk is as requested, is tell you about this database and give you a feel for what's in it and how it might be used by you to actually support the estimate of daily energy requirements. So the first thing that we faced was this big problem that pooling data across these studies actually turns out to be not that straightforward. And the reason it's not that straightforward is because the technique was first used in the 1980s in humans. And during the late 80s and early 1990s, there was some debate about the best equation to use. You need an equation to convert the mass spectrometry data on isotope content into estimates of CO2 production and hence total energy expenditure. So there's a key variable in that equation called the dilution space ratio, which is actually the ratio of when the isotopes go into the body at equilibrium, they give a slightly different estimate for the dilution space. And that's then the ratio of those two is called the dilution space ratio. So different people made different estimates from samples of the population and suggested then equations based on these different dilution space ratios. So I made a suggestion in 1993, Scholler made a suggestion in 88. There are other ones as well. So what happened, unfortunately, was there was no real clear consensus reached by the people using the technique about what the best equation was. And so individual labs continued to use what they thought was the best equation. And these equations actually differ by about 3 to 10%, depending on the elimination of the isotopes. And an increasingly big problem has been that in recent studies, people have not even said what equation they use. So it became quite difficult to pool data together across the different studies. So what we did when we set up the database was we got people to submit the baseline mass spectrometry data so that we could then use a single standard equation across all the studies. So then the question became, okay, now we've got all that mass spectrometry estimates, which equation should we use? Because then we're just in the same situation we were in the 1990s. Everybody's got their favorite. So we decided to use a different approach, and that was to use the database itself to redefine the dilution space ratio, because then we'd have about 7,000 estimates of the dilution space ratio. We did exactly that, and a paper was published in Cell Reports Medicine early in 2021, which contains that estimate of the dilution space ratio and also a new equation based on that derivation. So this is the new equation here, and that can be now used across all studies in the future, but also retrospectively in all these data in the database to provide a common estimate of total energy expenditure. So to check out how good that equation was, we went back over validation studies. So we found 61 individuals in validation studies, 61 adults, that is, and we looked at the average discrepancy between CO2 production in a respiratory chamber against the estimates using the different equations. And basically what we found was that the new equation performed just about the same as the reset equation. It's very slightly better in both the accuracy and precision. There's not really that much in it. So the reset equation seems to have been the best one, but these other equations produce various levels of error. So one thing you may be aware of is that the dilution space ratio depends on body weight. It's lower in infants. And so what we also did was, because we'd done this derivation of dilution space ratio on adults, that equation can't be used in infants. So what we did was we fitted a curve to all the data, including these data on very small infants. And then we can use that curve to substitute into the equation. And so we derived a more general equation that includes the dilution space ratio with the dilution space ratio defined by this curve, it's exponential in relation to body mass. And that allows this equation to then be used not only in adults, but also in children. And it also gives us space for future development as we understand more about the factors that influence dilution space ratio. And there's a big analysis of that going on at the moment, led by Bill Wong from Baylor. We wanted to check out how good that equation was in infants, of course. So there are lots of validation studies in babies. So this is a group of data for babies, and this is CO2 from indirect calorimetry against the exponential model, and you can see it works pretty well. So we recalculated all the data in the database with the new standard equation, and this is a comparison of the new equation for total energy expenditure against the values published in the equation. And reassuringly, there's actually a good relationship between the two, as you would expect, but there are outliers. So there are individual data from the originals that are quite a way away from the re-derived estimates using the standard method. And so I think we're able to get rid of some of that noise that's in the original data by using this common database, common equation. So in the second part of the talk, I'll tell you what's in the database. So there's going to be some tables here that are pretty boring, but it does give you a feel for what's actually there. So if you go into the database, this is what you see at the moment. So it was last updated in 2021, November 2021, that was version 3.4. And at that point, it contained 7,646 measurements of energy expenditure. Those are spread across 32 countries and 128 published studies. The youngest individual we have a measurement for is 8 days old. The oldest is 101 years old. And 51% of the data are for individuals between the age of 18 and 65. So this is the breakdown by country. This is a slightly updated breakdown using the very latest version of the database, which is slightly more data in it. So this is 7,668 values now. And if we look at the data where it's from, the majority of data in the database, 61.8%, is from the US. In the Americas, there's also a bit of data from some other countries in South America. There's no data for Canada, which was a little surprising. There probably is data out there, but it's not been submitted to the database. And the second largest group of data is actually from Europe. So if we look at across the countries in Europe, you can see there's some countries where there are particular groups like the Netherlands, the Maastricht group has submitted an enormous amount of data to the database. So the total for Europe is about 25.8% of the database. And so together, Europe and the USA are 87.6% of the data. So where do the other data come from? Well, there's about 7% of the data is from Africa. A lot of data put in there by Amy Luke's group. And they include some data from Tanzania, which are actually hunter-gatherers. And then in Asia, there's about 3% of the data from Asia, and that is mostly from Japan. And this group here from Nepal is actually a group of climbers on Mount Everest. So that's an unusual group. So having mentioned that there are unusual groups, how many data are in there for unusual groups? Well, there's about 40 measurements for professional athletes, 179 for amateur athletes, and then some data for non-athletes in unusual activity, like people climbing mountains or people running across America. And then we also have some data on disease status. About 3% have declared disease. So that's quite small, and that's probably because many of these conditions will have been screened out. So the database consists of studies where people have, so what we pulled in are non-intervention groups. So there are intervention studies that are in the database, but they only have the baseline measurements and the non-intervention groups. And so since most studies have exclusion criteria, probably a lot of disease status is screened out in the exclusion of those studies. So for example, we have relatively few people with type 2 diabetes. So that could be an underreporting issue, but it's also probably because people with type 2 diabetes are screened out of studies that are, for example, looking at interventions for weight loss. And then we have some data for reproductive status, although this is dominated by unknown status. So the majority of both females and in males is individuals of unknown reproductive status. So I've got on here what the status is. So pre-puberty, 248, reproductively active, but not actually reproducing at the time of the measurement is 396. Postmenopausal, about 1,289. Pregnant, there's a sample of about 131. And lactating, there's only about 20 individuals. And then for males, reproductively active, pre-puberty, post-puberty, but still under 18, a very small group, but a massive group where there's just no declared status in terms of reproductive status. And then I was asked to detail the publication status. So 381 of the data are definitely not published. 4,464 definitely have been published. And then there's this group where the status is unclear from the submission. And that's because the person submitting it put in a study number or a study code, but didn't actually say what that study was or whether the study had been published or not. So it seems likely that the majority of these have actually been published, and we can chase down these and then get to an absolute number of what's published and what's unpublished. So for 2,292 records, we also have measurements of basal energy expenditure. And so that allows us to calculate values of physical activity level, which is the ratio of TE to BE. So TE divided by BE is defined as physical activity level. So there are 111 records that have PAL greater than 2.5, and these are mostly athletes of people in unusual activity. 2,089 are for adults, and 686 of these are from the US. So if you just look at the histogram of PAL values, then what you can see is that the mean of those values is 1.77. The maximum 4.89, the minimum 0.73, which is obviously physiologically impossible, but that's the data that's in there. I did a small analysis of comparing the data for USA and Europe, which is quite interesting, because if you look at USA and split the data into adults aged 18 to 65 and elderly adults aged over 65, you can see in the US that the value for adults is about 1.73 and for elderly about 1.7, so a slight reduction there. But if you look in Europe, then you see that for most countries, with the exception of the UK, actually the PAL value is higher in Europe, averaging about 1.76, but the decline in the elderly is greater, going down to 1.53. So I did an analysis of that. I included fat-free mass as a covariate, which is significant, but this age effect is very big. And there's also a significant difference, very significant difference between USA and Europe, and a significant interaction. So it occurred to me that given the difference between Europe and USA, with Europe having higher PAL levels, and you being a committee based in the US, that you would be most interested in the US data. And so I've broken down what's in the database just for the USA data. I can do it also USA plus Europe if you want me to do that. But since there is a difference between USA and Europe, you may not be that interested in the European data. So here's a more detailed breakdown for the sample for the USA. So there's 4,741 values in there. It's very heavily dominated by females. So actually females are about 3 to 1 dominating the database. If we do this by age group, so I was asked to split it into infants. I wasn't given any actual guidance how you define these, so I've defined them by my own criteria. So infants I've got as 0 to 2, toddlers 2 to 5, children 5 to 12, and then adolescents, teenagers, adults 18 to 65, and then 3 groups of elderly in 10-year age classes. So what you can see here is that that dominance of females isn't very strong at all in the youngsters, but it becomes greater as we go into the adults, and it becomes much bigger, 4:1 in the elderly group. So this is the male sample by age and ethnicity. So I have ethnicities across the top. So this is African American, Asian American, Caucasian, Hispanic, not available, and other, which is generally mixed race. So then if you look at this data, what you can see, I mean, just generally, these are the absolute numbers in black and the percentages in red. And what you can see is that there's more diversity in the data for the youngsters. When you get up into the elderly, you can see that there's virtually no data for Asians and literally no data for Hispanics. But a big point to make is that 21% of the data actually has no recorded ethnicity. So ethnicity is not available for a large number. That status of no ethnicity gets lower as the sample gets older. So no ethnicity is a lower percentage in the elderly. And it's very clear that Hispanics are underrepresented, although that's less so in the young. And if you look at, so what I did was I recalculated them as a percent of the known and then looked at the US Census expectation. And what you can see here is 23% of the sample is African American compared to only 12% in the population. So African Americans are overrepresented. Asians are about on the spot, Caucasians are about on spot, but Hispanics are massively underrepresented in the database. So then if we look at females, this is the same data. I'll give you the slide so you can look at these numbers in detail later, but the same patterns are there. Actually, exactly 21% or also in the females have no ethnicity. No ethnicity gets lower in the as the subjects get older, and in the females as well. Hispanics and actually also Asian Americans are underrepresented. African Americans are overrepresented, and Caucasians are about expectation. So then I took the data for adults, that's age 18 to 65, and also for the elderly age 65 and over, and broke them down by BMI. So there's not really enough data to do this breakdown by BMI for the younger classes, and the elderly broke down into classes. So if we look at this, then this is for each of the ethnicities. And what you can see is the sample is pretty similar in relationship to ethnicity. There's no real massive differences. I mean, although the numbers look big there, it's because the sample size is lower for the Asians and for the Hispanics. But overall, we have a kind of pattern down here where most of the data is actually for normal body weight and overweight subjects. And then there's declining numbers as they become increasingly obese, with a very small percent that are underweight. So this is the same. This is the data for females. This is the data for males. Sorry, this is the data for elderly females. And what you can see is the pattern is very similar. So we have the elderly females at the bottom compared to the adults. So adults are 18 to 65, elderly are greater than 65. And what you can see is that the patterns are very similar for both the groups of adults, the middle-aged adults and the elderly adults. And then this is a table for the males showing the same thing. So this is all males for the adults, 18 to 65. And you can see the patterns pretty similar. In the males, overweight slightly more represented than in the females. So it's a flip about there, but the pattern in the obese is about the same. And then for the elderly males and elderly females, again, the patterns are coming out fairly similar to each other. But you can look at these tables at your leisure and ask me whatever you want about them. And then finally, this is both age groups divided by BMI. And for males and females, in the younger age group, 18 to 65, and in the elderly age group, greater than 65. And you can see they're broadly similar to each other. There's no big differences. So what I put down at the bottom here is the summary across all individuals in the database. So this is 3,839 adults. And what you can see, and this is expectation if it's a sort of random sample of the population. So this is NHANES 2015-16. And what you can see is that actually there's a slight overrepresentation of normal and overweight, and then a slight underrepresentation of the obese groups. But I think actually, considering this is a group that's been sampled from about 1990 up to modern day, and we're comparing it just to 2015, that's probably a pretty good random sample of the population. So I think it is pretty representative of what's going on out there. And then I'll just finish by just telling you about what's been published from the database. We had a big paper in Science in August last year that looked at daily energy expenditure through the human life course. TE obviously is mostly dependent on fat-free mass, but it also changes in relationship to lifespan. And we can take away the fat-free mass effect to get a normalized estimate. So this is the adjusted TE, and we get this interesting pattern that it's much higher during childhood than what you expect from the body mass. It's then completely flat between the age of 20 and 60. There's no difference once you adjust for weight between males and females. And there's also no indication of any change in relationship to menopause or middle age, where you would expect middle age spread. But then from about the age of 60, there's this very slow decline into very old age. And I think that's probably it. The key points then from that study, the life stages we thought might have a big effect, don't seem to. There's no effect of puberty, no effect of midlife, no menopause effect. The stability between 20 and 60 was a bit surprising, and then it declines at ages above 60. So on the behalf of the Dublin Leveled Water Database Management Group, I'll thank you for your attention. I'd be really happy to answer any questions. Thank you very much.
Thank you so much, John. That was a really great overview of the database. And we're open to any questions for Professor Speakman. Go ahead, Sue. You're on
muted,
mute.
Sue.
John, thank you. That was really helpful. I have a large number of questions actually, but let's just start with one, which is that as you know, we had a doubly labeled water database that we put together for the last DRIs in about 2000. Are all of those data points included in your new database?
As far as I understand, yes. So the main contributors to it was Institute of Medicine, wasn't it, that pulled it together, because National Institute of Medicine was IOM at that stage. And I think the main two people who put data in were Dale and Klaas. So that's data from the US and from Maastricht.
Okay.
And they're both major contributors into this database. So as far as I'm aware, that data will have come into the database. I think the sample size was about 2,000.
Right. Beth, do you have a question for John?
Yeah, thank you. That was a really interesting talk. And for someone who's not immersed in energy metabolism and whatnot, it makes a lot of sense. I had a question about study data quality and publication. Do you have any idea why some of the studies are unpublished or haven't given you the publication status? Are some of those rejected by journals, or they just haven't gotten around to it? And related to that, do you have any formal way of evaluating the quality of submitted studies?
So the reason there's a small number that are definitely unpublished is principally because they're recent submissions that have just not been round to being published yet. So there's at least a couple of those of my own studies. The unpublished studies come from the same labs that have got the published studies, and I don't think there's a quality difference between the unpublished studies and the published studies. It's not the case that these are studies that have been submitted and rejected because of some quality issue. The question of how we might evaluate quality of the submissions into the database is quite interesting. We've been through the database, we've cleaned up any data that might be glitchy because of typos or physiologically impossible data, like the deuterium coming out faster than the oxygen 18, which is probably just a typo in the submission. So we've screened out data that we're clear that it can't be true. But the data that's been published and the data that we're not absolutely clear of what its status is, it would be quite difficult to do a sort of rigorous check and say this data item is better quality than that data item. The reason why people submitted data against codes, it's potentially partially because of IRB regulations about anonymity in sharing the data. So if a lab has an IRB directive that they can't share that data's being put into a database, then they can only put it in against a code that says, like, you know, study 5 or whatever. So we can trace back those studies, and I can check whether that was the reason why the information wasn't given. My guess is probably 80–90% of those are probably published already. So I think, you know, it's worth a while doing that and finding out which of those are published and which are unpublished. But I don't think it's a quality issue that's involved.
Yeah, and if I can just add to that, John, I know a couple of those unpublished studies have subsequently been published, and sort of not in defense of the management group. This is a huge amount of data that came in very quickly. We don't have administrative or research assistant staff to help go back and sort of fill in those blanks. So, you know, I think that probably is a part of it as well.
Yeah.
Heidi?
Thank you, Dr. Speakman. That was an excellent and very clear. I really enjoy easy to follow presentations. I do have a concern, you know, that I thought maybe you could speak more to, which is that, you know, the US population is millions of people, and clearly, you know, this is an excellent resource, but it is less than 5,000 individuals, and a lot of it comes from certain segments of the population and certain specific labs. And so when we talk about trying to develop requirements for the entire American and Canadian population, I wouldn't call 5,000 people representative, they aren't. The studies were not done as representative samples pulled from the US and Canadian population. And so I do have a concern about relying too heavily on this data to develop equations for millions of people and, you know, public policy programs that represent millions of people.
Yeah, sure. I mean, I think that's a very valid point. This is a compilation of studies that were done for all sorts of different reasons. And the aim wasn't to get a representative sample of individuals. And clearly it's not a representative sample of people by race. I was pleasantly surprised by the distribution in relationship to BMI. I mean, I think there's acknowledgements to be made there. If you do use the database, it has flaws in its application to this particular project. but the problem is it's all we have. So I think at the moment, it's probably the best resource of double leveled water data that's available to you. I think one strength of the database is this fact that we've recalculated everything with a common equation, and that gets over some of the variability. If you go back to other original studies, then pulling data from those studies will have this potential error that we don't know what equation they used, and it's not possible to just recalculate it without the individual numbers in there. So I think we estimated that given the number of studies, if you just look in the literature, how much data is there out there? We figure there's probably about 20 to 25,000 data points available. And I think, so we've got about 8,000 and 5,000 of those are from the US. So my guess is we've probably got a quarter of what's potentially available in the world. So, I mean, it's, you know, there's a distance to go on that and there's more to do. But I think at the moment, this is what it is. And you know, you got to take it as it comes.
So Nancy, did you have a question for John?
I did, but I see some other hands up. John, I think one thing that I'd like your opinion, because you said maybe we're really interested in only the US data. In my view, we're not trying to describe the energy expenditure of the US population. We're trying to describe the range of human possibility, from very sedentary people for whatever reason, up to very active individuals. And so even though the European data is slightly more active than the US population, we certainly want to capture that with all the data that is available. So I would argue that we would want all the data as much as possible, probably eliminating extremes that aren't naturally, don't naturally occur in the US population, such as 14 days of military training. And after that, then it's up to public health agencies or even us to make a recommendation where we would see what level of physical activity is most conducive to health. And so in that regard, I think we really would appreciate the whole range of data from US, from possibly the Japanese data, and from Europe. So I'm just curious about your thoughts on that.
I mean, I only said that because I thought the remit of your committee was to define energy requirements for Americans and Canadians. If I got that wrong, then fine.
Well,
I mean,
it is our mandate, but
my assumption. Sure.
We are to address the populations, but it's to make recommendations for the populations. And I would say we would want to first reflect what's all possible and then home in on where we think it might be most desirable.
I mean, the database can't tell you that, of course. I mean, it's only got the numbers on it. It can't tell you anything about what's desirable or what's not desirable. But, certainly, the data is there for Europe and it's accessible and it can be analyzed. And I've shown you some of the analysis there. If I misinterpreted the remit, then, I'm sorry, but I can, easily let you know what's available for Europe as well, of course.
Yeah. That's great. Thanks, Sue. And then Janet.
Yeah, John, so you alluded to this already, which is that I thought one of the most surprising things in the science publication was the non-relationship between age and total energy expenditure once you adjust for fat-free mass between the age of 20 and 60 or 65. We've already heard from stakeholders that they're surprised that energy requirements were as high as they were in the previous DRIs. So certainly this change over time in energy expenditures is on my mind. And I have two questions in relation to that. One is, what's your explanation for that? Just how you're thinking. And the other thing is, I wonder if you adjusted for fat mass as well as fat-free mass, whether that relationship would change. You must have done that.
Okay, so I'll address the last point first. These are adjusted for both fat-free mass and fat mass. So the plot was just fat-free mass, but actually the adjustment is both. Okay. So the stability through time, I mean, if you look in that data, there's a lot of noise. And it's split into 10-year time segments. So there's plenty of scope, for example, for there to be a dip in menopause and it be missed in the data. So actually, somebody's already submitted a request to look at that in much more detail and look at year groups of ages of women and see whether there are really complete stability through that time period between 40 and 60. So the data's analyzed on a very coarse time frame, and I think there are possibly things in there that were missed. It is unexpected that there is that stability. I think once you get above 65, 70, the other problem is there's probably survivor bias. So if you have high metabolic rate and you die, then what's left to be sampled are people with lower metabolic rates. So I'm not really sure. I mean, there's a lot of problems there with that data that we, obviously we can't measure people that died, or we don't have any longitudinal data to evaluate whether that's the case. So whether, individuals that are measured at 65, we don't know what their mortality rates are. So I think it's cross-sectional data that we should very cautious about making any longitudinal inferences about. And I think that's probably where the biggest problem is. So when we start to talk about it's stable between 20 and 60, it's not really stable between 20 and 60. It has the illusion of stability from a cross-sectional sample.
John, I'm afraid we're at our end time. Janet, could you send John your question in the chat? Okay, that would be great. And I'm going to turn this back over to Anna Maria. John, thank you. That was really an excellent presentation. And thank you, for all the work you've done on the database to this point.
Okay, great. Thanks very much.
Right. And so I believe, Susan Roberts, you're going to be introducing our next speaker.
Yes. Before I start that, I just wanted to announce that unfortunately we are not, Dr. Leanne Redmond will not be able to speak this afternoon. She was our second speaker, so I wanted to let people know that. But our next speaker is Dr. John Jakuzik. John is a senior investigator and director of the population science at the Translational Research Institute at Advent Health in Orlando, in Florida. He was at the University of Pittsburgh for many years. And he's considered a leading authority on the benefits of physical activity for weight management. He has more than 230 peer-reviewed publications, many of them in high-impact journals, and a PhD in exercise physiology from the University of Pittsburgh. His title is of the presentation is Physical Activity and Long-Term Body Weight Regulation. Thank you, John.
Thanks, Susan. I just want to make sure I got the right screen up here. So share that. Can you all see this screen okay? Where I'm moving my okay. I just want to make sure. So thanks so much. I think I have 20 minutes to kind of tell you everything I know about physical activity and weight management and body weight regulation. So I'll try to move through this rather quickly, and hopefully we will have time in the panel to discuss things further. But I think that I want to talk about this not just from a weight loss treatment perspective, but touch a little bit on the prevention of weight gain and prevention of obesity as well, very quickly. And so as Rick Troiano, who's going to follow me, knows, we investigated this as part of the 2018 physical activity guidelines for Americans. And we did an extensive review on how physical activity might contribute to prevention of weight gain. And there's an entire chapter on this in the advisory report. But I want to point out a few things to you that came out of that report. And this is just one example of some of the data that we were able to look at. What we were able to find in this particular study is this was looking at the odds of maintaining a healthy body weight by level of physical activity. And in this particular study, healthy body weight was maintaining a BMI under 25 BMI units. So what you see here is that as you go across the spectrum of physical activity, the amount, the dose of physical activity, it appears that the odds of maintaining a healthy body weight under 25 actually are increasing. And in particular, out here at this level of this met hours per week. And so it's at a relatively high level of met hours per week where you see the greatest benefit for prevention of weight gain that will allow you to stay within this healthy body weight. And so it can basically comes down to the fact that we believe that activity is a critical component for prevention of overweight and obesity. In addition, we were able to find some data that examined whether or not physical activity might help to prevent the development of obesity. So even if you're already have modest overweight, does it prevent that from occurring? And this is just working in the opposite direction. But as you go across the spectrum, when you get out beyond 7 hours per week of vigorous intensity activity, that you basically see a nice reduction. But what's really important here is that you already start to see this drop in the likelihood of developing obesity, even by moving from a relatively underactive lifestyle to even some level of activity that's equivalent to 1 to 2 hours of vigorous activity. If you were to say, well, what does that mean when it comes to moderate intensity activity? If we could extrapolate, that would basically double that. That would suggest that maybe we need 2 to 4 hours of moderate intensity activity as opposed to vigorous activity to start to move the needle to prevent the development of obesity. And I think that these are really critical because so many times in our way of thinking, we're always thinking about the treatment of overweight and obesity and the long-term weight loss maintenance that comes with that. But this kind of pivots that a little bit and says, let's not forget about that primary prevention aspect where physical activity may be a key contributor to prevention of overweight or obesity. But a couple of additional things came out of the extensive review of the literature that we did at that time. One is that, of course, as we would have hoping and were expecting, that total leisure time physical activity was consistently inversely associated with weight change. So the more you did, the less likely it was for you to be gaining weight or the less weight you would have gained over a period of time. And in this particular review of the literature, we were looking at studies that contributed for over a period of 1 year of weight gain. So it wasn't like we were just looking at 3 months or 6 months. We found that the studies that actually examined moderate or moderate to vigorous intensity activity had a more consistent pattern with this inverse association with weight gain. It was harder to find studies of light intensity physical activity, but when we were able to find those, it basically was either not associated in a way that we would have expected. But again, there was very little out there in terms of light intensity activity, and that was one of the recommendations of a place we needed more work. But I'll have a couple additional thoughts about light intensity activity before my presentation is done today. Walking was not consistently associated with the change in weight. However, it appeared that you needed to get to a certain threshold of walking in order for it to actually start to attenuate weight gain. And when we saw the effect, we were seeing it in studies that were reporting greater than 10,000 steps per day. So it may be that we have, while there's some benefit to moving the needle, we might really need to get to a certain threshold in order for it to start to really have an effect on prevention of weight gain. We found that occupational activity in the few studies that we found about this was inversely associated with weight gain, but it was mostly in that moderate and vigorous intensity occupational activity. And we didn't see it where we had individuals reporting light intensity occupational activity. So whether or not that's an intensity factor or simply that intensity was contributing to greater energy expenditure, which was the factor, we were not able to determine. But it does suggest that maybe type of activity might have something to do with this prevention of weight gain. And we were not able to find that household activity by itself appeared to minimize weight gain. So when you start to separate it out into types of activity, modes of activity, the data become a little bit less consistent compared to the overall leisure time physical activity that we were looking at. So quickly moving on to what about weight loss, which is kind of in that treatment space as opposed to the prevention space. Well, there's been a number of reviews of the literature done, and so I don't want to start pulling out individual studies here. But in 2008 Physical Activity Guidelines report, we did look at this, and we found that the mean weight loss that comes from physical activity on average is between 0.5 and 3 kilograms when you start to examine physical activity. And we saw that threshold of weight loss occurring when activity was at least 150 minutes per week or greater. And there was no prescribed dietary change. So just telling people maintain what you're doing from an eating perspective, intake perspective, and you get people to become more physically active. The threshold appeared to be at this at least 150 minutes a week or greater. And in the studies that did not show a significant weight loss due to physical activity, all those studies at that time were under 150 minutes a week of physical activity. And probably, if I recall correctly, we're kind of more down near the 100 minute per week physical activity range. So again, there might be a threshold. But when we looked at the data more extensively, and we did this and reported this in the 2009 ACSM position stand, and as we looked at the data over time, it seems to kind of be consistent, but I use this as the reference. There does appear to be this dose response effect that when you're under 150 minutes a week, it really has minimal effect on body weight, probably some for some people. When you get over 150 minutes, you start to see this about 2 to 3 kilogram reduction. But then when you get much higher than that, up in this 220-ish to over 400 minute per week range, which is a lot of activity, you will see a much greater weight loss. And I have a couple thoughts about why it might not even be greater than that. One might expect that it would be in a few slides. So there might be a dose response. And again, I want to point out that this is without a prescribed dietary restriction. So when you then prescribe a dietary restriction, as is typically recommended for weight management and obesity treatment, what you tend to see, and these are just an example of data that we published in JAMA a number of years ago, but it is consistent, it continuously is consistent, that when you compare individuals who are prescribed dietary restriction and you give individuals that same dietary restriction, but you add physical activity to that, what you see is about a 2.4 kilogram additional weight loss compared to what you get with a dietary restriction alone. And that's about a 22% improvement. In this particular study, we were prescribing to progress to a 200-minute or more per week threshold of structured, moderate to vigorous physical activity that was unsupervised. So, and this is fairly consistent in the literature when you start to look at least 6-month windows of weight loss. However, there's a couple of caveats that I think need to be taken into consideration when you start to think about the effects of physical activity on weight loss. The first is that when we start to see this 20 to 25% additional weight loss beyond what you get with dietary restriction alone, it becomes very evident that those studies were using what we would consider to be more of a moderate reduction in energy intake. So these are studies where the dietary intake prescribed as part of the weight loss program was probably ranging in that range of about 1,200 to 1,800 calories per day. And those were targeted calorie intakes based upon initial body weight, assuming that people with a higher body weight have a higher metabolic rate and need maybe more calories. So it's in that about 12 to 1,800 calorie intake per day. However, when you look at the literature where that intake gets much lower than that, you start to get under 1,000 calories per day, 800 calories per day, and even lower when you start to think about very low calorie diets and some more severe caloric restriction, the effect of physical activity on body weight and changes in body composition starts to wash out. And so the effect that we see might be, it might be important to consider what the caloric intake need recommendation is when you start to think about the effect that that's going to have, the physical activity is going to have on body weight. Because when you get too low, there's a lot of other compensatory mechanisms that are kicking in that are kind of washing out that effect of physical activity. And so that's something that I would recommend that the committee really think about in terms of talking about energy expenditure and physical activity and its effect on body weight. However, as the title of this talk mentions, it's about long-term. And the place that I've been very interested in and the field is really interested in is how does physical activity contribute to the longer term effects on body weight regulation? In this particular case, weight loss. If you take a person with overweight or obesity, you try to reduce their weight, how does physical activity contribute? And I actually think that the bigger bang is probably in the weight loss maintenance phase or prevention of weight regain phase compared to the initial weight loss phase. And I say that, and this is based upon a number of studies. I'm just pointing 3 of them out here. We first came across this back in the late 1990s. And when you look at the literature, there's a few others prior to that that looked at that found this. And when we gave individuals the same weight loss program of dietary restriction and physical activity, and in a post hoc way looked at who was most successful, we found that the individuals who were consistently reporting over 200 minutes per week of structured physical activity were the ones who did the best long term. And when we look at the average, don't have it on here, but the average amount of physical activity done in this group was averaging about 270 to 280 minutes of structured activity per week. So it's it seems like it might be a fairly high amount of physical activity in this state of weight loss that might be important for the maintenance or the maintenance of weight loss or prevention of weight regain. Jeffrey and Wing showed the same thing. However, they saw some increase, but again, a higher level of activity was more predictive. And then we followed that up a number of years later and showed in another study the same type of thing. The one thing that's important to note here is all of these studies use self-reported measures of physical activity. And so there's some potential error going on here or bias going on here. The other thing that I want to point out, and this is hot off the press, it's currently in review at Obesity. It's in a resubmission right now. We completed a study where we actually randomized people to a dietary restriction alone between 12 and 1,800 calories per day based upon initial body weight, dietary restriction plus a moderate dose to progress them to 150 minutes of activity per week, that same dietary restriction or a high dose to progress them to 250 minutes of activity per week. And this is absolute change in body weight, percent change in body weight. And what we found in this study, and it's interesting because reviewers always say, well, of course, physical activity is going to let the person do better. Well, in this case, on average, we saw no differences in weight loss across these 3 groups. All of them lost weight, and all of them had basically about the same average maintenance of weight, at least over a 12-month period of time. What's also important, and I'm just showing the weight loss here again, but I'm plotting over here some of the data we have on change in physical activity. This is met minutes per week. You can see that the group that we asked to do more was doing more. But one of the challenges we face in these types of studies is that even though we ask people not to do things, some of them do things and they get a bigger response. So, but even in this case, both of the activity groups were doing far more activity than this diet-only group, far more, yet the weight loss was exactly the same, suggesting that I'll cautiously use the word compensation, whether intentional or unintentional, going on that's making up for this difference in this increased physical activity in these groups compared to these groups. The nice thing about this study is we did use objective physical activity monitoring using a device. So we have a lot more confidence that these data might be not biased due to self-report. But we've also taken a look at some of our data and this is where I think I'm going to mention a few things I think that are critical. We did a post hoc analysis of some data a few years back where we looked at how well people did at 18 months with their weight loss. And I'm just plotting that here as weight change and percent weight change. And you can see that this group right here has lost more than 10% of their weight by this period of time, and they're actually at around 16%. But we then took a look at the physical activity patterns in these different groups of weight loss to see what was potentially different there. And again, this is objectively measured. So the first thing we looked at was just total moderate to vigorous physical activity. And when you just take a look at this picture, you take that snapshot and you say, well, clearly what it is it's moderate to vigorous physical activity. The people who did better with their weight loss in a comprehensive program, dietary modification and physical activity, it's all about total moderate to vigorous physical activity. And one could conclude that from this slide. But I think that we need to think a little bit deeper as we start to think about this. And that is, I know this is busy, so I'll get you through this here pretty quick. This is that same slide, this slide right here, that's plotted right up here in this quadrant. same thing. However, what we then looked at was we broke out the physical activity into kind of smaller buckets. And what we did was we said, well, let's look at the moderate to vigorous physical activity that were done in bouts less than 10 minutes. Did the groups differ in terms of how much activity they were getting in bouts less than 10 minutes? And the answer to that was they were not. All the groups, no matter how much weight they lost, got the same amount of moderate to vigorous activity in bouts less than 10 minutes when you accumulate it all together. Where we did see the difference was in the bouts greater than 10 minutes, suggesting that the group that did better was doing more what I'll call intentional physical activity, purposeful physical activity that was sustained for 10 minutes or greater when they did it. And this looks very similar to the pattern in the upper quadrant. The other thing that came out of this was we actually, for one of the first times, we were able to objectively look at light intensity physical activity. And the other thing that popped out was that the group that did the best over time had this increase in light intensity activity that was sustained, versus the other groups started to see this decline in light intensity physical activity, suggesting to us that it's not just about the moderate to vigorous physical activity. It might be about how they get that moderate to vigorous, but that we shouldn't be saying, well, take your light intensity activity and just start converting that over to moderate to vigorous, and you're going to be successful. I think what this message is add light intensity physical activity to your day and increase the amount of moderate to vigorous physical activity you do. And both of those in combination seem to be adding to the energy expenditure and making a difference. And we've actually followed this up recently. I'm not going to show the slides, where we showed the same pattern in more current studies that again showed this contribution of light intensity activity, not as powerful as moderate to vigorous, but definitely a contributor. The other thing I think that needs to be taken into account is the variability in response to a physical activity program on body weight. We see this all the time. These are data published by Joe Donnelly and colleagues, where with the same amount of physical activity prescribed for men and women in terms of minutes per week, you can see the variability in weight loss achieved in the men and the variability in women. Unfortunately, half the women lost or gained weight, some gained, and this was not muscle mass gain. This was mostly an aerobic training program. That we did not see that this was a muscle mass gain. This was actually real fat gain. Most of the men lost weight, but there's great variability there. And the question is why? You know, we come up with a recommendation, but we still have variability we need to take into account. Well, one of the reasons that I think that might be happening is this metabolic equivalent task. We talk about it as the MET, which is, you know, one MET is a certain amount of energy, and you can expand upon that. You know, 2 METs are 2 times the resting level, 3 or 3 times the resting level. And there are these estimates of energy energy expenditure with the MET. You know, whether it's absolute oxygen consumption relative or 1 calorie per kilogram of body weight. And then we also then start to think about these MET categories where we say, well, this is light intensity, this is moderate, this is vigorous. And not that I disagree with this, but I want to poke a few holes in it that might need to come into consideration. And that is, for the first thing is the MET level. If we look at this category down here, you know, is light intensity, moderate, and vigorous the same for everyone? Well, it's actually not if you were to look at their fitness level. If you have a person who's very, very unfit, at 4.5 METs, which is considered a moderate intensity, they're actually near maximal activity capacity. That's actually vigorous for them. Out here, 6 METs for this individual is moderate, but for this individual is still light. And so as we start to think about how the MET is used in terms of derivatives of physical activity and the energy it costs that goes with them, we also might need to think about this in terms of, is it practical for people to actually be at these different levels when we start to think about this? The other thing is, how accurate are these estimates that we give to the MET? And what's its implications? I'll just quickly show you that when we've measured energy expenditure in women, these are women with overweight or these are adults with overweight or obesity, men and women. We find that the caloric expenditure for equivalent to resting for a MET is far under what it would have been based upon the estimate. And for men, it's about right. But then you start to look across this, and this is the resting absolute energy expenditure. Again, it varies depending on body size, and it's not always at the threshold that you think it's supposed to be at. And so when you start to think about what would that mean in terms of overall energy expenditure, if you were to assume that the estimate or non-estimate, the white level here is if the energy expenditure for 60 minutes of physical activity, these are females, these are men, using the estimates of the MET versus the actual measured METs, if we were to use those for 60 minutes of moderate intensity physical activity at 3 METs. You can see great variability, and you start to ask, then you say, well, why are we getting variability in the weight loss response? It's probably due to some of this variability that's going unaccounted for. The other part of this is, and it gets back to, I appreciate Dr. Speakman's presentation, that, when we measure something objectively with doubly labeled water, it doesn't always line up very well with self-reported data. But the vast majority of the information in the weight loss literature is on self-reported physical activity data. And so we need to be doing a better job and be careful about how to interpret those data as well. And finally, just really quickly, the other factor is the dose response issue. Like how much dose do you need in order to change body weight? This is a study I was fortunate enough to work on with my colleague, Joe Donnelly. And it's a good example of this where we had control individuals and exercisers. And these individuals, the exercisers, were exercising 45 minutes a day, 4 to 5 days a week for 16 months in a laboratory supervised. And the controls were not. And when you look at changes in cardiorespiratory fitness, it's exactly what you would think. For both men and women, the people who were exercisers had a greater increase in cardiorespiratory fitness, so it should have worked. However, when you look at the weight change data, for men, what you see is that exercise dose actually caused a weight loss. For women, it actually prevented weight gain. This is the exercise, pretty flat line. The controls were gaining some weight, and here's the men losing weight, and the controls were staying relatively flat. You're like, but wait, we prescribed the same time and intensity of physical activity, and that's the problem. Time and intensity varied because the men were burning at about 600 calories per episode, women were burning 400. So in a follow-up study where we randomized people to 600, 400, or control, what you see is when you look at that over 9 months, that these are the controls, men and women. The 400 yellow here is men and women, and then the green is men and women. The 400 men and women lost the same amount of weight. The 600 calorie men and women, even though it looks like it's different, it's not statistically different, lost the same amount of weight. So it's about the energy expenditure that they had, not prescribing activity of 30 minutes at a moderate intensity. Depending on body size and things, you need to actually get to the right energy expenditures. And this pattern of variability, I think, also needs to take into account that physical activity and exercise do not happen in a silo. They don't happen in a silo all by themselves. This again is that variability we saw in the Donnelly study. We followed that up with an acute exercise study in our laboratory where we had them come in and do an acute bout of exercise or a control day. And we found that in response to that acute bout of exercise, half of the individuals ate less. We had them have an eating episode afterwards. Half of them ate less in response to that acute day. Half of them ate more in response to that acute exercise day. So if this is true, half the women gain weight, half the women lose weight in response to exercise, maybe the women that are gaining weight are increasing their intake in response to exercise versus some women are decreasing their intake or not compensating. So we need to be taking into account that activity does not happen in a silo. And that there's all these parameters that happen around this that we need to be thinking about, which I won't get into, but Blundell, King, and others have really done a nice job of talking about this information. And then finally, just the final word here, and this is really kind of new, but when people are physically active might be important as well. This is recent data from Willis and colleagues who looked at some data in terms of who lost weight in response to exercise. And what they found was that the people who lost weight in response to exercise are those individuals who got most of their exercise, the majority of their exercise was done during the morning over the intervention period. Those who were inconsistent or got their activity later in the day didn't lose as much weight. And so it may come down to whether or not is that, well, they were just then more compliant, or was it that that's having an effect biologically on individuals? Was that doing something to the eating side? We're not sure, but there are data coming out suggesting that the timing of activity might be as important as to the amount of activity that one does. And so just as I finish, I think that we need to be taking into account the variability that we see in weight loss. and weight change due to maybe the metabolic equivalence that we're assigning to things. We aren't accounting very well for light intensity activity, but I think that there's a contributing factor there we need to take into account. We need to be thinking about both the relative and absolute intensities that we're asking people to do this activity at. I think that there's information about the pattern of activity that matters, and whether or not activity is contributing to energy intake differences or energy intake patterns. And the one thing I didn't have time to get into is also, as we take a look at individuals who are overweight or with obesity, their efficiency of movement is very different than a lean person. And then when they lose weight, that efficiency changes. And so I think we need to be looking at that efficiency issue and how that contributes to overall energy expenditure, as well as people move through their various stages of body weight status. So with that, I'll say thank you very much for your time today. Appreciate it.
John, thank you very much. We are going to move straight on to the next speaker and then take questions for both speakers afterwards. Our next speaker is Dr. Rick Troiano. Rick was recently a program director in the risk factor assessment branch of the Epidemiology and Genomics Research Program at NCI's Division of Cancer Control and Population Science. He's promoted the validation and use of accelerometry-based devices for the assessment of physical activity in research and population surveillance. He was also on detail to the Office of Disease Prevention and Health Promotion as coordinator for the development of the 2008 Physical Activity Guidelines for Americans. And most recently, he was a member of the Guidelines Development Group for the 2020 WHO Guidelines on Physical Activity and Sedentary Behavior. Rick has a PhD from Cornell, and the title of his presentation is NHANES and Physical Activity. Rick, thank you very much.
Thank you, Susan, and thank you to the committee for inviting me to present to you today. Control of my slides is over at your end, so I hope somebody's going to pull them up. There we go. Okay. Full screen there, and there we go. Okay, so I'm going to, the next slide, please, Melanie. I'm going to really just cover two topics, make a few comments on the value of device-based measures, as well as raise a few caveats about device-based measures. And then I think mostly what the committee wanted to know about is some of the data that are available from NHANES, and I'm going to focus on the two cycles between 2011 and 14, where we have device-based measures of physical activity. Next slide, please. And you can move right on to the next one. So I'm going to highlight a few studies that just give you some thoughts about why device-based measures, I think the easy way to describe this is to say, give a much stronger signal for physical activity than does self-report. And John made reference to some of the concerns about, John Jakisik made reference to some of the concerns about self-report. So this is an older study using the NHANES 2003 to 2006 data, where we just looked at the cross-sectional associations between minutes of physical activity in bouts at that point, from self-report on the left column and from the device measures on the right column. And you know, we have our systolic blood pressure, BMI, HDL cholesterol, glycosylated hemoglobin, glucose, and insulin, and just want to call your attention to the magnitude of the beta estimates and the statistical significance that you see a quite stronger association from the accelerometer-based devices. Next slide, please. And again, this is a paper that came out just a little over a year ago. It's using the step count from the accelerometer in NHANES 2003 to 2006. And we looked at, it's been long enough now that there's some more mortality follow-up there. And if you go to the next slide, what you see is that these associations are so strong that reviewers don't believe them. So this paper, that I hope nobody on the committee was the reviewer who said, it's just not possible that, you know, this is the kind of reduction in mortality you're seeing from step counts. And I'll point out that, you know, about the same time and since a couple other studies and other cohorts have shown very similar associations between device measured steps and mortality. Next slide, please. And then another benefit of physical activity, and you know, John Jakisik's comments about timing of activity relate to this, I don't know if the committee is going to go this way, but you have precise time resolution both in duration, which this paper looked at whether or not bouts of physical activity measure versus shorter accumulations, but you also have timestamp data. So you can theoretically divide up the clock day and look at when people get their physical activity. And in this paper, what we showed is that really, in terms of the mortality reduction, it did not matter so much whether you acquired your physical activity in bouts of 10 minutes or more. It was really the total volume of physical activity that measured. But also kind of as a comment to one of the data slides that John Jakisik presented, if you are going to get high total volumes of physical activity, you pretty much have to do some bouted activity. You can't really get to the really high amounts just with kind of sporadic activity. And moving on again to the next slide. This is a paper that I imagine many of you are familiar with, but it's one that is an example of where we do have data on both double labeled water and device-based measures, and it provided an opportunity to look at the association between those metrics. I believe this data is probably part of the pooled database from the measure studies. These data are from the Harvard cohorts. And if you go to the next study, or next slide, please. What I wanted to point out from this study is just the fact that what Andrea Tomastek found is the strongest association between the double label water measures and the devices were when you looked at the total daily activity. This is part of a table 3 that looked at the association between total activity and moderate to vigorous physical activity in minutes and other kind of subsets of it. But it really, not surprisingly perhaps, is that it's the total activity per day that is most strongly associated with the both the total daily energy expenditure and the physical activity energy expenditure. And next slide, please. I know about half of the committee members, and I know this is ridiculously basic for you, but the other half, I don't know where you are in these areas. So I'm just going to make a few points so we know we're all on the kind of same starting point. And this is, I just want to point out with this slide that the accelerometer devices measure exactly that acceleration. And the main point to make about this is that they don't account for things like resistance. And actually, I think that's on the next one. I guess what the point I'll make here is that the signal that we get from the device is just acceleration. And when we're interested in converting that to something like physical activity or energy expenditure, you need to make use some kind of algorithms to do that. And as I move into talking about the enhanced data, one of the challenges is there is no consensus algorithm for some of the measures we're using, particularly across all of the population groups that are covered in enhanced. Move to the next slide, please. So here's where I was going to point out that, one of the really benefits of physical activity, as John Jakisik alluded to, is you take out the reporting aspect. You are actually measuring the physical ramifications of the physical activity behavior. And for our purposes in being interested in total energy expenditure, you get all physical activity, not just the intentional, not just the occupational, everything is there. Now that's a blessing and a curse because you don't know exactly what the context of the physical activity that is occurring is from the device measures alone. You would need additional information to get that. And then for the most part, in almost all the studies that are going on or exist now, we tend to measure acceleration at one body part. And so if that device is placed on the waist or the hip, it's primarily measuring locomotion, or now, as is more common, if it's worn at the wrist, it's measuring upper body movement, which includes the ambulation, but has some additional both effort and noise. But most importantly for this committee is to point out the fact that none of these measures take account of resistance. So walking up a hill and walking on the flat look pretty much the same to a waist-worn accelerometer. as well as walking up a hill with a backpack on. So as somebody pointed out, these are not measures of METs directly. Next slide, please. Okay, so with those few comments, let me move into the NHANES data, primarily the accelerometer data. Next slide. Again, I don't know everybody here, so if you're not familiar with it, the NHANES is a nationally representative sample that is conducted on the civilian non-institutionalized population. It includes all ages in the population now. It oversamples minorities, and the target is about 5,000 individuals a year. And if the sample weights are incorporated into analysis, it is therefore representative of the US population. Next slide. So the accelerometer protocol in the 2011-14 was done on ages 3 and up, but that started in 2012. So we have complete data and publicly available data on ages 6 and up, and then from 3 and up starting in 2013 for the publicly released data. I didn't mention it in here, but there was also a National Youth Fitness Survey that was done in 2012, and there are accelerometer data from those 3 to 15-year-olds that can be combined. The device was worn on the non-dominant wrist. The participants were asked to wear it for a little over 7 days. They received the device. It was put on their wrist in the mobile exam center. So you had a partial day on the day they were examined and a night. They were asked to wear it 7 complete days and then to mail it back on the after they woke on the 9th day. So we have, with full compliance, we have 7 continuous days and 8 days of sleep. It was a GT3X Plus from Actigraph, and data were collected at 80 Hertz. There's also Lux data, which measures light exposure. Next slide, please. All right, and go ahead. So over the 4 years, we had over 16,000 participants who agreed to wear the device, which represents about 88% of all eligible examinees. And we had very good compliance from participants with over 95% devices returned. This analytic N is for a paper I'm going to describe in just a slide or two. We brought it down to just under 15,000, which is the numbers you see here for female and male youth and adults. And some of those exclusions were had to do with issues with the algorithms that I'll go into in a moment. Next slide, please. So this is the paper that was fairly recently published out of those data. Colleagues of mine and I developed reference curves for the total activity counts from the wrist-worn device. Next slide, please. Move ahead. There we go. And the metric that we used is called Monitor Independent Motion Summary Units. This is, for those familiar with it, it's similar to an actigraph count, but it's not a proprietary metric. And there is software out there that will allow it to be calculated from other raw acceleration type devices. And there's a reference there for all the details on that metric. We worked with collaborators at Northeastern University to process the data for NCHS. They applied algorithms for when the device was being worn while awake, when it was not being worn, when it was being worn during sleep. However, similar to the comments I made about cut points for devices, the studies that allowed the development and calibration or validation of these algorithms were quite small and far from representative of the age range that's included in NHANES. So there's a lot of caveats in the documentation about these algorithms. And in terms of the exclusions, some of the exclusions, we use these for the exclusions where we saw non-wear more than 5%, which was 72 minutes a day, and sleep more than 17 hours. And that's a little striking. And what I think what that represents is there's a fair amount of misclassification by the algorithms between non-wear and sleep, which is probably not too surprising. We included anyone who had at least one valid day And as you see there, most people had about 5 to 6 days across the sex and age groups. And then the curves were generated using GAMLIS, generalized additive models for location, scale, and shape. For those of you who've worked with growth charts and BMI, this is kind of a evolution of Tim Cole's LMS method. And we ended up using a Box-Cox T distribution to adjust the data. Next slide, please. And this is what you get. And it was interesting to see John Speakman's energy expenditure curves from the article on the pooled data set, because they look a lot like this. Not, perhaps not too surprising. So you see the highest level in youth, and then it's relatively flat between about 36 and 60, and then a fairly rapid decline. And just spend a moment here. So what we have are the percentiles going from the 3rd to the 97th of the total daily MIMS units by age and sex groups. Next slide, please. So a few points to make about these data. It is a total daily activity metric, which, as I mentioned, represents everything that anybody is doing, anything that resulted in movement of their wrist, and or their full body with their wrist. It includes all intensities, and perhaps frustrating, I know frustrating to a lot of people, is there is no easy way to quantify physical activity by intensity. There are cut points for actigraph counts. They cannot be just routinely applied to these MIM counts. They're not identical. There are certainly associations between the two metrics, but you cannot apply a cut point from counts to the MIMS. And as I've said here, frustrating to all of us is we still don't have a consensus on cut points across ages. And as you all are very well aware, I'm sure the percentile values are very valuable for a lot of applications. And I think, perhaps when the committee is working on estimating across the population, even though we don't have energy values for these physical activity metrics, I think that the relative population levels will be very helpful in the modeling. Next slide, please. Just quickly, so you're aware of it, the data kind of working from the right back to the left. What we published on are using the daily summaries. All of these data are now available from NCHS, both the daily summary and then what I call the intermediate data, which is the minute and hour level summations, are available to be directly downloaded from the NCHS NHANES website. And then just at the end, just a couple of days ago, really, the raw data are now available. The link is on the NHANES website, and it takes you to an FTP site to download the data there. Because the high volume, there's a separate file for every hour for every participant. So not for the casual data analyst. And next slide. Just a couple comments on self-reported data, at least the data that are available in the same 2 cycles of NHANES. The physical activity questionnaire that was used is based on, fairly identical to the WHO Global Physical Activity Questionnaire. It was filled out or responded to by participants ages 12 and older. If you're not familiar with it, that questionnaire asks participants about a typical week and asks how many days in a typical week, and on the days you do it, how much time you do it. Do you do activity at work, travel to and from places, and recreational activity? And for work and recreation, there are separate inquiries about moderate intensity and vigorous intensity. The data sets then assign a MET value to the responses. So 4 METs for the time spent in moderate and 8 METs for the time spent in vigorous. And a summary metric of MET minutes per week is provided. And I think that's my last one. Go on to the next slide. Yeah. So I think now we have time for some questions.
Great, thank you very much indeed. Thank you to you and thank you to John. we now have 23 minutes for questions for both speakers. If you could put up your hand, your sign, raise hand sign. I'll start with a question for John. No, actually, Janet, you were trying to ask a question before. Janet, go ahead.
Thank you. I had a question for Rick. Thank you for your presentation. The question I have is whether work has been done that relates the physical activity level that you get from the ratio of TEE to BEE from these doubly labeled water type of studies to other metrics of physical activity that you talked about, like step counts or minutes of moderate and vigorous physical activity, and if there is any type of correspondence that's been described?
That's a really good question, Janet. I know that the data are there to do that. I am not off the top of my head, and remember, I retired a few months ago, so my head's getting fuzzier. I'm not aware of studies that have directly looked at that. But for instance, in Andrea Chomistek's paper, that could be done. You know, they now in those studies, I think they have just estimated resting energy expenditure, you know, based on an equation, not measured. But you could certainly, you know, with that caveat, you could look at PAL levels and some of the metrics they got out of, in their case, a HIP-1 accelerometer.
Thank you.
Anna Maria?
Yes, thank you. Thank you both for wonderful presentations. John, I was very curious, and I wanted to probe you a little bit more about the sort of realization of the fact that for sure there are compensatory mechanisms that are taking effect that allows for differences in weight loss. And one of the things that intrigued me was this new observation of the fact that METs are different for males and females. And so the intensity of that exercise is different. How could we take that into account for our work?
Wow, that's kind of a loaded question, and I was hoping I'd tell you guys to deal with it, and I'll just tell you to deal with it. I don't know if I have a great answer for that, but I think one of the things that would be very thoughtful of this committee to at least put some thought to is the fact that I think that the energy expenditure for the MET, at least in our hands, and I think you'd want to look at the literature more broadly to see, you know, kind of what's the variability there, might help to explain some of the differences that we see in response to these interventions for men and women. It may contribute also to how much might be needed to prevent weight gain. And, you know, it's unfortunate, I mean, I'll put the caveat that it may be, you know, for in the study that we did with Joe Donnelly, the women actually had to be active for a longer period of time to get to the same energy expenditure. So depending on how you all start to think about activity, if it's about caloric expenditure or it's about this equivalent of time to get to this caloric, you might need to really make that clear that that there are these that at least bring that point forward. I think that would be very important to do that. Okay.
Heidi.
Thank you both for excellent presentations. Dr. Troiano, one thing I noticed, the slides went by quickly, but I think I noticed in one of the slides that the decline in energy expenditure or the decline in physical activity seemed to start at a much younger age in males than in females. You had that slide where it was across ages and it was separated by sex. Mm-hmm. I wonder if you've, you know, perhaps have any insights on why that might occur.
So yeah, I apologize for the rapidity, but I figured you're going to have the slides and the papers are out there to study, and I just pulled it up on my screen. Actually, the decline among youth for both girls and boys really starts about age 7. There really doesn't seem to be a big sex difference there.
I was referring to adults. there was a difference in, there was a slide where the females were on top, adult females and adult males, and it looked like the decline started around age 60s, but the males, it looked like the decline started around age 40s.
You're right. It does. It is a little steeper at about age 48, actually, kind of somewhere in there. But the one thing that to be careful of, I guess, is I know with me, my eye is drawn to the top line, and the 97th percentile is a little more bouncy than the median. But they are, you know, and really both of them are pretty stable until, yeah, there's slight differences. But, so I'm not going to try and explain it because I don't know how much of it's really real.
And then I had a sex-related comment for Dr. Jakicic. I think the sex differences in both presentations are really fascinating. And one thing I'm not sure if it was mentioned in terms of the sex differences with regard to the METs and energy expenditure, and particularly the variability you showed, the extreme variability in women in terms of ability, you know, from weight loss to weight gain, where there was variability in men, but it was more about the amount of weight loss. There wasn't so much weight gain in men. And I think maybe, you know, the propensity for men to have more muscle mass and the propensity for women to perhaps have, you know, more subcutaneous fat may be a factor in that huge variability among women, and really, you know, has tremendous meaning for clinical practice in terms of success of weight losses, particularly for women.
I mean, I'll just quickly comment, and that variability was the study that used the same time duration for men and women, and it clearly, and so the variability, that if you look at the shape of that variability, it's the same. But you know, I think you're right, and I think that, you know, many studies of weight loss have really focused on, you know, go out and take a walk, you know, do the aerobic things. And what I didn't get into was the age issue as well. As we get into, you know, 60s, 70s, we need to be thinking about something maybe more than just walking, and getting at the point that you're talking about with the preservation or the preventing the reduction of lean mass that might be contributing. So resistance training things and so on. So I completely appreciate your comment that it's not one size fits all, for sure.
Nancy.
I have a question for John. John, can you reconcile the differences? Can you reconcile the differences that you're seeing across studies for the effect of walking? For a while there, it was highly recommended for everyone to get out and at least walk. You did not see an effect on prevention of weight gain in the study you presented to us, whereas we saw dramatic effects on mortality. And I'm just wondering what your committee's thinking in terms of public health recommendations when it comes to walking. And I remember the database on volunteer weight loss, what people said, the most common thing they did was walk. So where do you stand on that as far as making recommendations for the public?
No, it's a good question. And remember that those data were looking at prevention of weight gain or prevention of overweight or obesity. And I think the one thing that Nancy doesn't come into account there, and there was a threshold of 10,000, right? But maybe what's not coming into account is what's the baseline that people are at. You know, if a person has a lifestyle, a job, whatever, that's getting them 6,000 steps already a day, you know, maybe it's the delta that we're looking at as opposed to the absolute number. And those studies looked at the absolute, but I would not throw the baby out with the bathwater, because it is the easiest thing for most people to do. And I think it's about how we couch the message for individuals, that's one contributing factor. And in particular, as I brought up that light intensity factor about how maybe that's important, the easiest way for people to get a lot of light intensity activities is just get up and move around throughout the day without thinking about intensity. So I'd be careful about saying walking doesn't work. It's maybe about the delta or the threshold.
Anna Maria.
Yeah, I just wanted to follow up on Heidi's comment and trying to understand a little bit about the differences between the sexes. In the studies that you presented, that you had diet restriction plus physical activity, and we saw these differences between men and women. Do we know the composition of the diet? And I know we're going to get into this a little bit later, but I was just wanting to ask that of those particular studies.
I can tell you that most of those studies will report what the prescription of the composition of the diet was. I know that's what we do. And in most of those studies, Anna Maria, they're using self-report food frequencies or something that's, and they'll report on, it was X amount of this or X amount of that. You got to take that, you guys, some of you know way more about that than I. So that there are data in there around that. One of the things that we found in our studies of the successful, I'll call them successful losers, is that it seems to mimic like that kind of general public health, kind of idea of, about 50% carbs and, less than 30% fat. But the one thing that we see in the people that have done best with weight loss is they're up at a protein intake, self-reported, of about 20% or so. So it's a little, at the time was a little more than what was kind of being recommended. But the data are there if you wanted to take a look at it, but it is mostly self-reported.
Thank you.
Susan Barr.
Again, thanks for the presentations, really informative and very interesting. I was also intrigued by the walking and the step counts, because Rick showed a really, well, he indicated himself that it was almost an unbelievable impact on mortality from the 10,000 per day step count, yet it didn't seem to be linked to body weight per se. So I'm wondering if, we're getting into a situation where BMI or overweight obesity has an impact on health, but the impact on mortality may not necessarily be associated with weight change. So all those data for impact on other biomarkers other than BMI. And I just wondered if either of you could comment on that, and how we disentangle weight from other health parameters.
Right. I'll say something, and I'm sure Rick might have something to say as well. I'll make two very quick comments. One was we also published a paper on our weight loss data that actually looked at step counts, not just activity. And I could send that paper along. I think we published that in 16 or 17. And we did the same thing there where we looked at the total step counts, but then broke it out. And from a weight loss perspective, the individuals who were the most successful at weight loss absolutely were getting more steps. And they were up at that 10,000 step threshold. But just like our other activity data, we broke it out by, did they just kind of move around, or did they get it in bouts? Did they do it moderate to vigorous? And the same pattern was there, is to get to that 10,000 step count, you needed to be doing some, as Rick pointed out, some purposeful activity. I can send that paper along. You might find that to be intriguing. The other thing I think that's important is separating out the health risks from the mortality. We just published a paper that came out in Diabetes Care from the look ahead data, and it wasn't step counts per se, but early on in that study, we saw a lot of changes in risk factors and so on and so forth. But when we looked at the predictive value of physical activity on the hard outcomes of cardiovascular health, we only saw those, we didn't see those after 1 year of physical activity predicting what happens downstream. We found it after 4 years of activity predicting downstream. So the effects on mortality might take longer than the effects on risk factors, which might be some of the kind of minutia that we're getting into here as well. I don't know, Rick, if you have something to add to that.
Well, the one thing I wanted to add is to be careful of the magic 10,000, because in our study, and actually it kind of relates to John's comment about the delta. Most of the studies that have looked at mortality are, it's a hazard ratio compared to something else. So in our case, what we commented on, kind of where the curve really starts to bottom out, is at 8,000 compared to 4,000. I think in IMIN's study, it was even a bit lower in older women. So, in terms of what Nancy was asking about for the public health messaging, it may not take an incredible amount of walking particularly depending upon where people are starting from. Now, none of our cohort data are interventions. They're not looking at a change within individuals. It's comparing different groups. But yeah, I guess and to the weight mortality issue, I guess the other thing is, you know, that the mortality benefit can happen to people who are still overweight as well.
Okay. One other real quick thing I want to add, if I can, to that, Sue, and that is, and I'll mess it up, but there was a review paper done on steps a dozen years ago or something. And, you know, give people a pedometer and see what happens. And when they gave people a pedometer, it increased their step counts by about 2,200 steps a day. And over a period of time, it actually showed a modest reduction in BMI with just an average increase in steps of 2,000 steps a day. So it gets at that delta issue that Rick was just talking about. That might be the most important thing.
Thank you. Ethan.
Just to add to that, I'm wondering about the, you know, probably the fact that you can't disentangle the confounding that people who choose to, you know, walk more, purposeful walking, purposeful activity, are also probably making lots of other changes to their lifestyle, most of which you probably either aren't, you know, collecting information on and might not even be able to collect information on, including changes in what they're actually consuming.
Mm-hmm. Yeah, Ethan, I think that one thing that we've talked about activity as maybe being a gateway to a constellation of behaviors that contribute to health, as opposed to it being the be all end all. And that's that disentanglement that goes on. I think you're hitting on a really important point, is that, you know, individuals who are engaging in physical activity may be electing to do other health related behaviors that are also contributing to the benefits that we're seeing. So I would agree.
Yeah, quite a few years ago, David Berrigan and I did a paper where he tried to look at clusters of behaviors in NHANES, and you know, you definitely see kind of groups that do everything wrong or do everything right, but a whole bunch of people kind of mix and match it.
Beth.
Yes, thanks again for two great talks. I have this question for both of you relative to NHANES, because it appears that John had experience trying to use it for the dietary guidelines and Rick has had experience actually using it. If we were to think about making a recommendation that future NHANES should include some measures of physical activity, what would you recommend? Rick mentioned something about having some preliminary data analysis from data that's already there. And then what types of measures would you recommend be included? And is it even worthwhile at this point in time, given the state of the science?
Rick, I'll let you handle that one.
I knew you were going to do that. Well, you know, some people have asked me, you know, are you continuing to do the device measures in NHANES? And, you know, I don't know how many of you picked up on the fact that the data that were just released were, you know, completed collection about 7 or 8 years ago. And so the short answer to your question is I would certainly encourage device-based measures. But before we just jump back in and collect, you know, thousands of data points, I think we really need to help the field advance to where we know how to use those data. And that's why, you know, when NCHS came back to me while I was at NCI and said, you know, do we want to fund it again? I'm like, not yet. So we need to wait on that. The other barrier, and I hope this is less of a barrier now, is the data volume that you get from these devices is incredible. And the fun fact that I love to tell is the 4 years of accelerometer data that I just described to you, in terms of data volume, is more than all the data NCHS has ever collected in NHANES over all the years of NHANES. And so every time we've done device-based measures, we have pushed their frontiers in terms of how to handle with that much data. And the fact that they were able to pull off having an FTP download recently was a major win, because until a couple months ago, the plan was you were going to have to send in a brand new hard drive, you know, several terabyte hard drive that they would then put the data on and send it back to you. So I think the technology has caught up, and hopefully CDC has caught up with the technology. But I think that the weakest point is getting the field to move along to the point where we have a consensus on how to interpret those data.
I would agree.
We're about out of time. I want to thank the speakers for just terrific presentations. This has been really helpful for the committee. We've had many questions in consequence. Is there any last thing that both of you feel in the last 2 minutes that you would like us to know that hasn't been brought up?
So I'll just say, one, thanks everybody for inviting us. This, I think, is great that you're doing this. This is complex, as Rick just pointed out. And I'm a firm believer that activity is a key contributor to all these health benefits. However, I also am a realist to understand that there are other factors that contribute. So, physical activity is a great pill, but all these other factors, as you all think about this, need to be taken into account to really help us understand how to move physical activity forward and from a health perspective. So I look forward to seeing how you guys interpret all of the things that we've said and the work that you'll do.
Thank you.
I'll just end by saying, please feel free to reach out to me if there are further questions related to either what I said or what I didn't say and that you're curious about. And thanks again for the invitation.
So thank you, everybody. Anna Maria, do you want to close up the session?
Yes, thank you so much. I really appreciate our two moderators for this morning and our speakers. You gave us a lot to think about and precisely the type of information we were looking for. Once again, we will be reconvening back at 1 o'clock. And as Dr. Roberts mentioned, Dr. Leanne Ridman will not be able to join us due to an illness, but we will continue with our other speakers, and maybe we need to get out and get a little bit of exercise. So thank you so much. We'll see you at 1. Okay, let's go ahead and get started. Hello, I'm Anna Maria Sigaris, and welcome back to our open session for the committee to review the DRIs for energy. I'd like to remind everybody that this session is being recorded and it will be posted soon thereafter on the project website. We will be having a couple of speakers this afternoon. Unfortunately, Dr. Leanne Redmond will not be able to join us, so she will not be on the agenda for this afternoon. Our committee members are poised to ask questions of the speakers, so we will not be entertaining speakers from anybody else participating. And we look forward to a very interesting discussion this afternoon. And let me ask Dr. Heidi Silver to please introduce the speakers for this afternoon. Thank you, Heidi.
Thank you. It is my pleasure to introduce Dr. Kevin Hall. He is the section chief of the Integrative Physiology section of the Laboratory of Biological Modeling at NIH's Institute of NIDDK. And his lab conducts both human and rodent model experiments to look at the effects of human metabolism in response to diet and physical activity interventions, and also to develop mathematical models that help explain the results from diet and physical activity interventions on human metabolism. So I welcome Dr. Hall, who will be speaking today on the impact of dietary macronutrients on energy metabolism.
Thanks very much for the introduction, Heidi, and thanks for the opportunity to have this discussion with the committee. There was actually a little bit of discussion in the previous session about whether or not macronutrients, the composition of the diet, in even a more broad scale, impacts energy requirements. And so I hope that some of our studies and some of our analyses that we've done will be informative to the committee. We heard many years ago, there was a promise that very low carbohydrate diets might allow you to lose weight and keep it off, even if you're eating very many calories. And the idea was that you could eat more calories even than you were eating before you went on this diet. And as long as no carbohydrates were present, and still lose weight. Atkins' new diet the original diet revolution back in 1972 was promised it to be the high calorie way to stay thin forever. And of course, the only way this could happen without breaking the laws of physics would be for such very low carbohydrate diets to induce a metabolic state that had the body producing or consuming very many more calories in terms of energy expenditure. And so I became intrigued by this idea because it's persisted to the present day. And I'll show you some data that bear on that topic. But one of the things about the Atkins diet, as you all know, is it's a very, very low carbohydrate diet. And so one experiment that we did several years ago was to bring 17 men with overweight and obesity into a metabolic ward where they stayed for a continuous period of 2 months. So 24 hours a day, 7 days a week. Where we controlled their diet in a very precise way, a metabolic diet prepared by our dietitians. And over the first several days, they were spending 2 days a week inside respiratory chambers, so we could measure their oxygen consumption, carbon dioxide production, and thereby calculate their energy expenditure, as John Speakman mentioned this earlier this morning, but this time with respiratory chambers. And then we matched the energy that was provided to these people on the metabolic ward to what they were burning inside the chamber. And then for the next period of time, the last more than 2 weeks, on this baseline diet, which was a high carb, high sugar diet, 50% carbs, 25% of total calories coming from sugars, they switched to a isocaloric ketogenic diet with 5% carbs, 80% fat, and importantly, the protein amount was clamped throughout this last period of time. And so the hatched bars here are the 2-day periods where we pre-specified, we were interested in seeing this high calorie way to stay thin forever. Compare the last 2 days on the chamber on the low carb ketogenic diet with the last 2 days on the baseline diet, where they were consuming the same number of calories, the same amount of protein, but a very different carbohydrate to fat ratio. And during the period of the introduction of the ketogenic diet after day 0 here, you can see that there was a substantial shift towards burning more fat. This is the change in the 24-hour respiratory quotient, which is the ratio of the CO2 production to oxygen consumption. The lower that number is, the more fat that you're burning, the higher that number is, the more carbs you're burning as a relative proportion. And you can see that there was a very rapid and persistent shift to increase fat oxidation in response to the introduction to the ketogenic diet. In terms of our primary outcome, however, there was no significant effect on 24-hour energy expenditure in the chamber, as measured again on those last 2 chamber days on each diet. But when we looked at every single day that they spent on the diet, because they spent 2 days per week every week, they spent 2 days inside the respiratory chambers, we saw this small and transient increase in energy expenditure upon the introduction of the ketogenic diet, but that tended to drift away over time so that there wasn't much of a difference compared to the baseline diet. But nevertheless, I think this was real, and one possible reason why that might have occurred is because even though protein content was in the diet was constant, they went into a transient period of negative nitrogen balance, likely as a result of increased gluconeogenesis. And we know that gluconeogenesis is an ATP requiring process and therefore costs some energy. And perhaps as people transitioned away from that, transitioned into the ketogenic diet, they required more gluconeogenesis for the brain. But as ketones ramped up, that contribution may have dissipated over time. Of course, that's just speculation. And then one of the interesting things that we also observed was fat mass changes, as measured by DEXA, actually slowed down during that first period of time on the ketogenic diet. And that was related to the amount of negative nitrogen balance. So it seemed like, at least in the early stages, some of the energy deficit was swapped out for protein as opposed to fat in that early period of the ketogenic diet. We did another study, which was this time a randomized study within the same subjects, where people again spent a pair of 2-week periods this time with us at the NIH Clinical Center Metabolic Ward. And after a 5-day eucaloric baseline diet, we either randomized them to a 6-day reduced carb diet selectively or reduced fat diet selectively, and again spent several days inside our respiratory chambers. And then after a 2 to 4 week washout period, we repeated another inpatient period again for this 2-week stay. And in this particular case, the diets were selectively restricted. So in other words, what we did was we took these 19 men and women with obesity, and in one occasion, we selectively cut 30% of their baseline eucaloric needs selectively from carbs, keeping fat and protein at the eucaloric values, as opposed to in the other period of time, we selectively reduced fat, keeping carbs and protein at baseline values. So this is a head-to-head comparison of the effects of selectively cutting carbs versus selectively cutting fat. And again, in our respiratory chambers, we observed that the reduced carbohydrate diet, very much like the previous case, led to a rapid and persistent decrease in the respiratory quotient, and indicating increase in the amount of fat that was being burned. And then interestingly, in the reduced fat diet, nothing happened to the respiratory quotient. So it stayed very stable, despite the fact that 30% of the fat calories in the diet were being removed. The energy expenditure changes were again small, but there was only the reduced carbohydrate diet in this case led to a slight decrease in energy expenditure. Now, this is not getting to ketogenic diet levels. This was ended up being about a 27% carbohydrate diet. So although ketones definitely went up in the blood, they did not go up to very high levels as you see in ketogenic diets. And interestingly, we found that in this case, we saw a relatively small but highly significant reduction in body fat. So fat loss in the same people occurred to a greater extent with the reduced fat as opposed to the reduced carbohydrate diet. Now, I would say that, while this is highly statistically significant, this is, practically meaningless. You would not be able to observe this in the real world. These are very, very small changes that could only be detected on a metabolic ward where you're controlling every morsel of food that these people are eating and measuring their fat oxidation rates very, very precisely in our respiratory chambers. And in fact, when we then later went to do a systematic review and meta-analysis of all of the controlled feeding studies, not necessarily in metabolic wards, but where all food was provided, some were metabolic ward studies, others were not, that matched for calories and protein, but changed the ratio of carbohydrate and fat in the diet. What we saw was that body fat changes, indeed, very much like our data, were very, very slightly greater with the reduced fat diet as compared to the reduced carbohydrate diet. Now, the pooled weighted mean difference from this 2017 paper, is highly statistically significant, but I would again argue that this is, physiologically and clinically meaningless, small effect size. So only about 16 grams per day different between these isocaloric and isonitrogenous diets. So this is a great case of statistical significance, not meaning much from a practical standpoint, in my opinion, anyway. Now, since this meta-analysis was published, there has been another controlled feeding study with the same amount of protein, this time looking at very low carb versus low fat isocaloric diets. And they go along with what we observe more or less, no significant diet group differences over a 6-week period in this particular case. What about energy expenditure? Well, in 2017, when we did this, the same meta-analysis and systematic review, we again found that there was a very slight, again, I emphasize very slight, but statistically significant pooled weighted mean difference favoring low-fat diets increasing total energy expenditure. In this case, it was only about 28 calories per day. So again, I would argue that this is a practically meaningless difference between the two. But since this 2017 paper, there was a large, relatively large, these are all relatively small studies, given the that all food is provided, and these are controlled feeding studies. But there was another study that was included in an updated meta-analysis, and the results of that meta-analysis were slightly different. They basically matched what we found for the groups as a whole, but they then decided to segment the data into shorter versus longer term studies. And their conclusion was that lower carbohydrate diets, while they transiently decrease energy expenditure over the first period of time, there is larger increases over longer periods of time, indicating that it might take some time to adapt to these lower carbohydrate diets. And the main reason why they observed this difference was the inclusion of a study that had been published since our meta-analysis. This is a study that was published in the BMJ in 2018 by Kara Ebeling et al. And the idea of the study was, it wasn't to look at people in weight maintenance. It was basically designed to look at people after they'd lost a certain amount of weight. And so they had this run-in weight loss phase, and then people were assigned to one of 3 different kinds of diets: a high carbohydrate diet, a moderate carbohydrate diet, or a low carbohydrate diet. And these diets were then the calories in the diets were designed to kind of keep them weight stable over the next period of 20 weeks. So a very long study. It was an outpatient study. This was not a metabolic ward study. And the primary outcome here was to look at energy expenditure changes as measured by doubly labeled water. Now, the interesting part about that is that they have, as indicated at the bottom part of this, they have a pre-weight loss doubly labeled water energy expenditure measurement. They have another energy expenditure measurement after these folks had lost weight. And then they have 2 test phases at the midpoint of the 20-week intervention and at the end of the 20-week intervention. So before the actual test phases, there's actually 2 potential points of comparison. There's the pre-weight loss period, and then there's the post-weight loss period. And the BMJ study says that the pre-weight loss period, rather than the post-weight loss period, was originally pre-specified in the registry as the anchor for calculating the change scores. But they said that this was an error. But they never reported the results of the pre-specified analysis. They only reported the results of the changed changed endpoint. And so we downloaded the data and analyzed it in both ways. And this was a study that we did with John Speakman. And this was the main point of that original study, the result that they found. This is plotting the change in energy expenditure between the high carb group as compared with the moderate carb and low carb group. And this is the data that had shifted that meta-analysis result for the longer term studies. So what you see is that, there's an impressive increase in energy expenditure of 250 calories per day on the low carb compared to the high carb group. So that's a pretty substantial difference. And we were very interested in that because indeed that would explain, an increase since this was a larger study that was used over the long time frame. But interestingly, when you analyze the data according to their pre-specified a pre-weight loss anchor point, the results are much more modest, around 100 calories per day or so, a little bit less, and not statistically significant. So which anchor point you choose to look at kind of can sway you in terms of the magnitude of this effect. A couple of other points that are interesting to think about in terms of indirect calorimetry. This is very much like the Weir equation that John Speakman pointed out earlier. This is how you calculate energy expenditure based on measured amounts of oxygen consumption, VO2, versus carbon dioxide production, VCO2. For the doubly labeled water method, as Dr. Speakman mentioned, you are actually estimating with the isotopes the rate of carbon dioxide production, and you need so this is what you're measuring with the doubly labeled water method. And John showed you some various updates to the equations to measure that. But then you also then need an estimate of the respiratory quotient. And that can be a little bit tricky when it comes to comparing diets that are varying in carbohydrates and fat. As I showed you, when we put people in the metabolic chamber, the amount, this ratio can change quite markedly when you adjust the carbohydrate to fat content in the diet. And in fact, when we look at the data in terms of just the CO2 production, there is no significant difference between any of these groups when you look at the CO2 production. So everything hangs on the respiratory quotient that is assumed in this particular study. And it wasn't measured. I think that's an important point. It was not measured. But even when we measure respiratory quotient, so for example, here's the last 2 weeks of that ketogenic diet study that I started out talking about, where I showed you no significant differences in the energy expenditure from the chamber. When we naively use the measured respiratory quotients in the chamber and looked at doubly labeled water, it was very impressive. Now, these were exploratory measures, and as far as we know, this is the first time both chamber measurements and doubly labeled water have been conducted over the same time period, although this was not meant to be a validation study. But again, we saw, wait a second, this is a pretty big difference in energy expenditure as measured by the doubly labeled water method, which was different from the chamber. But when we then realized that we had to adjust the respiratory quotient for the state of energy balance that the subjects were in, the effect essentially disappeared. And this is when we had respiratory quotient measurements inside the chamber for which to adjust. In the Ebling study, they assumed that the difference in respiratory quotient was given by the difference in the food quotient between the diets that were provided to people. Unfortunately, their data also showed that even though these folks were on average weight stable over the 20-week test phase, they were only providing them with roughly 400 calories per day less than the number of calories that they were providing in the food, indicating that the subjects must have been eating off-study food. And so what we hypothesize is that a more realistic difference in respiratory quotient to use in the doubly labeled water calculations is probably about 0.07 for the diets that were used in that study between the high and the low carb group. And that cuts the effect size roughly in half and is marginally significant at a p-value of 0.11. And so when we did that reanalysis and then updated the long-term effects of the long-term meta-analysis, we find that it's still significant, but it's probably only about 70 calories per day or so, or about less than the energy equivalent of an apple per day. I'm going to shift gears a little bit because I think that the more interesting phenomena, in my opinion, is not on the energy expenditure side of things or the body composition side of things. As I kind of have showed you, my impression is that those are very small effect sizes. But how does diet composition affect how much people want to eat when they're not trying to change their weight? If you just kind of give them instructions, eat however much or little that you want, but we're going to manipulate the foods that are available to you. And so we've done a couple of studies now looking at those kinds of questions. Again, inpatient studies where we can measure quantitatively exactly what people eat. And so here's a 28-day inpatient metabolic ward study where we provide people with double the number of calories that they would be required to maintain their body weight and give them instructions to eat as much or as little as desired. They're told this isn't a study about weight loss or weight gain. They shouldn't be trying to change their weight. And on one occasion, we give them a diet that's about 10% carbs and 75% fat. And on another occasion, it's the reverse, 75% carb, 10% fat. And the question that we were interested in was, given these diets, did people eat differently in terms of their ad libitum energy intake? And what we found was very large effects. So we found that these same people, when exposed to the low carb diet, ate about almost 700 calories per day more than the low fat diet. So huge effects in this study. And they were blinded to, again, the primary outcome of the study. They were blinded to their body weights. They wore loose fitting scrubs the entire time, so they couldn't tell if their pants or clothes were getting looser. And not surprisingly, they lost more body fat while they were on the low fat diet as compared to the low carbohydrate diet. Interestingly, they lost more fat-free mass, which we suspect is primarily water weight, although they did go into slightly negative nitrogen balance on the low carb diet. And so even though they're blinded to their weights, if you just look at the weight changes, the daily weight changes here, it appears that despite eating 700 calories per day more, they are actually losing more weight, especially over that first week on the low carb diet compared to the low fat diet. So maybe Atkins was right after all, the higher calorie way to lose water weight over a couple of weeks or so. But it can be very misleading to people because like I said before, the fat loss was greater with the lower fat diet. So I kind of want to switch gears from the macronutrients for a minute and get away from some of the diet wars that have been going on between low carb and low fat camps for decades and decades, and turn again to another study, which is looking at diet composition and its effects on intake, because one of the things that we know about both of these camps of folks who recommend low carb versus low fat diets is that they also recommend that people often increase their intake of whole foods and especially non-starchy vegetables. They also have in common that they also recommend people reduce their intake of so-called ultra-processed foods. And I can talk a little bit more about what that means, but we use the NOVA categorization system from Carlos Montero to categorize ultra-processed foods. And so what we did was we decided we were going to do a very similar study design as the last study I just showed you. Again, inpatient, where people spend 4 weeks with us and randomize them to either an ultra-processed diet followed by an unprocessed diet or the reverse order. And the diets look quite different. You can see them on your screen here. The meals that we presented to people were actually matched for some of these nutrients of concern: the calories, the carbs, the fat, the sugar, the sodium, and the fiber. They were basically given the same instructions as the previous study: eat as much or as little as you want. This isn't a weight loss study. You shouldn't be trying to change your weight. Again, people were blinded to their body weights and whatnot. And our primary outcome, again, was mean daily energy intake differences ad libitum. And so this was what we found in that study. Again, very large effects, 500 calorie per day difference between the ultra-processed and the unprocessed diet periods on these diets. And unlike the last study where, on average, there was no weight gain on either diet, this study, we actually found that the people, when they were on the ultra-processed diet, gained weight, whereas when they were on the unprocessed diet, they spontaneously lost weight. And in fact, that was reflected by the changes in fat mass via DEXA. So they gained body fat during the ultra-processed diet, and they lost body fat during the unprocessed diet. So far in our hands, the only diet that has led people to gain weight and gain body fat when basically told to eat however much or little that they want is an ultra-processed diet. Low fat diets, low carb diets, they led people to lose weight and lose body fat, albeit at different amounts. But this so far has been the only diet that we've looked at that caused people to spontaneously consume excess calories and gain weight. And so just to summarize what I've shown you, and again, these are very small studies, they're highly controlled studies, but they're very small. And so, with all the caveats that go with extrapolations to representative populations, I'm sure we'll have some discussion about that. My interpretation is that isocaloric variation in the ratio of dietary carbohydrate to fat has pretty small effects on energy expenditure, and the methods that are being used matter quite a lot. Doubly labeled water is a great method for free living people, as John Speakman mentioned. But if you're comparing differences in diets where that respiratory quotient is expected to be different, the estimates are quite sensitive to your choice in the respiratory quotient, and very few people actually make those measurements of respiratory quotient. I also would say that the variation in dietary carbohydrate to fat, isocaloric variation has small effects on body fat mass. You can detect them, but only under very, very highly controlled conditions. But there are large effects on metabolic fuel utilization. I showed those huge effects on respiratory quotient. So you are changing which fuels are being burned, and there are substantial changes in circulating hormones and metabolites, which may be important for health. And I didn't have time to show those to you today. The other aspect is that diet composition has actually large effects on ad libitum energy intake in our hands. And that we found that these very low carbohydrate diets result in greater energy intake than very low fat diets, but only the ultra processed diets resulted in spontaneous weight gain and excess calorie intake compared to unprocessed diet that were matched for various nutrients. And I should point out that that the macronutrient composition there was about 50% carb, 35% fat. So kind of the typical sort of standard American macronutrient distribution. So with that, I will close. Thank the various people who've obviously contributed mostly to this work, and hope we have some time for questions.
Thank you, Dr. Hall. Let's see. Does anyone have any questions at this time? If not, I'm going to ask you if you might speak a little about your paper, Is a Calorie or Calorie for Calorie, that was published in Cell Metabolism.
Sure. So that was I think the second paper I presented today. That was the one that basically did the randomized order inpatient study with the selective reduction of carbs versus fat. So the main outcome of that paper was the differences in respiratory quotient and fat balance. And the main result, as I presented today, was that only the reduced carb diet led to a shift towards increased fat oxidation. But when you also account for the fact that fat intake was unchanged from the eucaloric state, and that in the alternate diet, fat intake went down and respiratory quotient stayed constant, the net balance was such that very slightly more body fat was lost during the reduced fat diet compared to the reduced carb diet. Now, the design of that study was related to those outcomes, but was related to the question about whether insulin plays the predominant role in regulating how much body fat was lost. And in that, what I didn't present today was that only the reduced carbohydrate diet led to a reduction in 24-hour insulin secretion as measured by 24-hour C-peptide in the urine. Both diets led to reductions in fasting insulin, which was interesting. But it turned out that you could lose body fat despite not changing your 24-hour insulin. You didn't have to cut carbs in your diet to lose body fat, and in fact, you lost slightly more body fat with the reduced fat diet as compared to the diet where you reduced only carbs.
And I'm wondering if the mathematical models that you've done support, because if I understand correctly, you're essentially saying a calorie is a calorie, right? There's really not a major significant difference, certainly not a clinically meaningful difference between the low fat and the low carb diets in terms of weight loss and energy expenditure.
In terms of body fat loss. So weight loss tends to fall, because of the water content and maybe a little bit of transient nitrogen imbalance. Sorry to interrupt you, by the way.
That's okay.
Yeah, that's right. For those outcomes, when you control for calories, but the last half of the talk that I just gave is that, of course, most people aren't controlling for calories in their day-to-day life, right? And they can't count calories. And even when we try to self-assess people's calorie intake, researchers can't do a very good job of that either. And so I think that this is a really key point, especially for this committee when it comes to making these recommendations, that yes, when you do these extremely well-controlled studies and you do these metabolic diets that are, prepared by our dietitians, where we, do as good of a job as possible and chemically analyze the foods and all this sort of stuff, we can detect very slight differences. But you're right, for the most part, it seems like if you keep the amount of calories constant and you keep the amount of protein constant, and you vary carbs and fat, you can detect very small differences in energy expenditure and body fat. but they're very, very small, and but other outcomes like insulin levels and glucose excursions and triglyceride levels and LDL cholesterol and ApoB and all the different subsets of lipid, those all change quite markedly. So it depends on the outcome of interest, I think.
Yes, I'm curious about the ultra processed versus processed diets. You mentioned that you did look at calorie levels, fiber levels, macronutrient composition levels, even though the foods were different. And in your list, you also included sodium, but I'm curious if the sodium content really was very well matched between the ultra and non-processed diets.
Yeah, I mean, we have that. I can look that up and provide that information. They were matched what was presented to people. And similarly with calories, was matched what was presented to people. However, people would choose to eat however much or little they wanted, right? And so what people chose to eat, and in particular, I think that you're right, that what people chose to eat in terms of sodium was quite different between the two diets because, mainly because of the snack portions of the diets. But I'll have to go back and look into that. I haven't spent a lot of time thinking about sodium, but the sodium that was presented to people was quite similar.
I apologize. I did something happened with my screen. I didn't see that those hands were, and so I'm not sure the order of the hands, but I'll ask Susan Roberts to please present her question or comments.
Hi, Kevin. I enjoyed your talk as always. I'm just wondering the extent to which consumed fiber and perhaps lower palatability in the low-fat diets contributed to the slightly favorable effects that you saw in that group. I mean, but in our hands, both palatability and fiber, probably have effects on energy expenditure.
So you're talking about, which study are you referring to, Sue?
I'm talking about the studies in which you saw, I wouldn't speak to which one, slightly increased energy expenditure in
okay.
low carb diets.
Oh, slightly. So yeah, so when we controlled for calories and change, yeah, so there are differences in fiber, and I don't think we, because they were not ad libitum, I don't think we even assessed palatability in those studies. We certainly assessed palatability in the studies which were ad libitum, and people reported the diets being equally palatable. Of course, that's just self-report, doesn't really get at the full, the full picture of food reward, which is, to a huge extent, below our conscious awareness. But they didn't report any of either of the diets being more palatable than the other when we asked them. And we actually excluded people who didn't find a certain amount of the foods familiar. So they had to rank the familiarity of the foods to avoid any neophobia. But I'm not aware of but there certainly was differences in fiber content in the controlled, the isocaloric studies. But yeah, we haven't tried to analyze the data to see how much fiber content may have contributed to energy expenditure per se, or body fat changes.
I would love to see that. I mean, we see I think 50 calories a day, something like that, effect of doubling the fiber intake from a typical fiber intake to a recommended fiber intake on resting energy expenditure.
Oh, that's interesting.
We have a question or comment from Susan Barr, please.
Hi, Kevin. Wonderful presentation. I love your studies. One of the things the committee was asked to comment on in our deliberations is energy requirements for weight loss maintenance. And I wondered if you would speak to us briefly about that.
Yeah, no, it's a great question. And it raises this issue. So I think it raises a couple of very interesting issues. One was that that study by Ebling et al., you might have noticed, was actually a weight loss maintenance study. And so another view is that maybe some of these effects of, very low carbohydrate diets kind of manifest themselves in that state of weight loss maintenance. so that's a possibility. I don't know the answer to that question. We haven't done studies on weight loss maintenance per se, but I think it's a very interesting question. And I know that Sue is involved in an NIH-sponsored study that's going to be looking at that shortly. But yeah, so as far as, there seems to be some debate about whether or not there are greater than expected reductions in total energy expenditure once people have lost weight and you've adjusted for fat mass and fat-free mass after the transient period of weight loss is over. In other words, once you've given people a long enough period of time to restabilize at a lower weight. And so some studies suggest that that does happen. Other studies suggest that that doesn't happen. There aren't a lot of longitudinal studies that have addressed this. There's a lot of studies that have said, okay, let's take a control group of people who have never had obesity, but are matched for the group of folks who have lost weight. There's very little data that look at people before they've lost weight, measured their total energy expenditure or resting energy expenditure or both, and then after they've lost weight. The Ebeling study that I just showed you is one example of where they've actually done that. And so the data are limited in that regard. And then there's this intriguing question about whether or not physical activity per se can actually influence resting energy expenditure. So I don't know if Herman Pontzer was mentioned in the beginning of this when we were the first part of this, but there's these intriguing data about very physically active groups of people who, when you use doubly labeled water and metabolic cart to measure their total and resting energy expenditure for wide ranges of objectively measured physical activity, once you've adjusted for their body composition, there doesn't seem to be much difference. And the question is, how is that possible? Something else must be adapting, and it's probably not reflected in just that isolated resting energy expenditure measurement, which is taken over a 30 to 45 minute period in the overnight fasted state. So this compensation, potential compensation, and whether or not it shows up in a resting or a total energy expenditure measurement, I think is a really interesting question, which I don't think we have firm answers to at this point.
Anna?
Yes, thank you. Kevin, I really appreciate your talk, and though I'm going to have to study those slides because you went through the material really fast to be able to keep up with everything, but no, it was wonderful. So I've got two things that I'm curious about to ask you. One is, back in the day, and I'm not going to say when back in the day, I do remember hearing that even small differences in calories and the small differences that you described of 63 to 74 calories a day makes up a substantial amount of an impact if that happens over a repeated number of days in order to result in a weight loss or a weight gain. Is our thinking different here now? Because you're basically telling us, that difference really doesn't mean anything. It's statistically significant, but it really doesn't mean anything.
Well, so let me give you an example, because I think that sort of thinking neglected several factors. And I'll give you an example of a study that we did in an analysis we did in collaboration with some folks I know at Johnson & Johnson, who had a randomized placebo-controlled trial of SGLT2 inhibitors for type 2 diabetes. So SGLT2 inhibitors are these kind of a relatively new class of compounds that basically increase the amount of glucose spilled in the urine. And so that can be thought of as an energy sink, right? So you're now spilling more glucose. It's like increasing your energy expenditure, although it's not expenditure per se, it's loss of calories. And that loss of calories amounts to about 300 calories per day. So a pretty big change in calorie, quote unquote, expenditure. And that is persistent. I mean, these drugs keep working. They don't have a waning effect over time. And the nice thing about this being a placebo-controlled study is that, people don't know whether or not they're on this stuff or not. And so, as opposed to exercise, right, which, you know you're exercising or not. And so a 300 calorie a day difference, that should lead to a huge amount of weight loss, right? I mean, that's according to that old line of thinking, right? But that old line of thinking typically does not account for several factors. One, which was the subject of a lot of my earlier research, which was how does energy expenditure decrease as people lose weight and as they lose fat mass and fat-free mass, and how does the cut in calories, if they're doing a cut in calories, how does that affect, the thermic effect of food and adaptive thermogenesis, and how does that play out both during weight loss and then potentially weight loss maintenance? And so we've developed mathematical models of that. And that turns out to be the minority problem. The bigger issue is how appetite increases as people decrease their body weight. And so in this reanalysis with the folks at Johnson & Johnson, basically we showed that their energy intake was going up over time to offset that loss of calories in the urine, so that they ended up losing a very, very small amount of weight. They did lose weight. In other words, you kind of have to lose some weight for this effect to kick in. But it's like a third or less of the amount of weight that you would have predicted, even after accounting for those changes in energy expenditure I just told you about as people lose weight. So the idea that a small change, even if it's persistent in energy expenditure, could translate into very, very large changes over periods of time, neglects those two factors. One is the dynamic changes in energy expenditure that occur as people lose weight, and secondly, the changes in appetite that occur as people lose weight.
Thank you. That helps resolve my other question.
Nancy?
Kevin, I have a question regarding the RQ. As you know, we plan to use doubly labeled water, and in the calculation, as you start out, we have to assume an RQ in free living populations. And from your presentation of your own studies, it looks like the choice of the RQ in a normal free living population is going to have a pretty minor effect on energy expenditure. So can you address the application of how to derive the RQ when you're using the doubly labeled water when there's no indirect calorimetry measurements?
Yeah, no, it's a great question. And, there's been there's been a long history of people looking at how to look at changes in body composition and back calculate what, if you know something about the diet and they're in some state of energy imbalance and therefore your body fat may have changed, trying to estimate how the RQ might be different than the food quotient. And of course, the food quotient is often estimated based on self-reported measures. And I think that, and John Speakman and I have talked about this a lot. For most people, if you're not trying to do a diet intervention that's changing the carb to fat content of the diet, or you're not trying to compare a group of people that have very different carb to fat contents, is probably not a big deal. And it probably gives you, people have shown that it's a valid method, and choosing an FQ of something like 0.85 for weight stable people is pretty good. But I think that where you run into trouble is where you get into these questions like I was addressing today, where you're really trying to compare groups that are not necessarily in energy balance, so they might be losing weight or gaining weight slowly, and more importantly, have very different ratios of carbs to fat in the diet. So the FQs are supposed to be different, and it's especially bad, I think, when people, the advantage of the doubly labeled water method is that people can be free living and you get a nice average CO2 production over a week or two period. But the disadvantage is that even if you provide people with all their food, and Sue Roberts had a very nice paper in the first phase of the calorie study where people, are going off their diet even though they're being provided with all their food. And so there's this off-study food question, which then gets to, well, what the heck are they eating, and what's the food quotient of the off-study food that they may or may not be accurately reporting?
Do we have any other questions or comments for Dr. Hall? I think Dr. Speakman has a question or comment.
It's not really, it's just a comment to follow up about this RQ issue. We have in the database information on what each of the studies used to transfer the CO2 production into total energy expenditure. So generally people are using this assumption of 0.85, but also there are some people who have FQ estimates and they use the FQ estimate to do the conversion, but we can provide that information about how it's been estimated.
Thank you. Well, I'd like to thank Dr. Hall for a really interesting and insightful presentation. I too plan to go back and look over the slides of all our speakers today and take more time and thought with them. I thought all the presentations were just fabulous, and thank you all.
Great. Thank you.
Yes. So I will go ahead and close the session, and once again, repeat our thanks to all the speakers. We know we gave you very short time to come and present to us, and you were fabulous, and it really will inform our work. And with that, I am going to end the public open session and ask our committee that we come back in 15 minutes, so a little bit after 2 o'clock, maybe 2:05, and then we will get finished with our closed session. So thank you very much, everybody. We appreciate it.